Hello there, and welcome to Science for Sleep, where curiosity settles into something soft and easy, and where enormous questions can drift gently through your thoughts without stirring anything too sharply. Tonight we're taking a slow step into a part of the universe that can feel almost too large to imagine, yet we'll explore it in a way that lets you unwind rather than puzzle or strain. You and I are going to look at two of the most unimaginably heavy objects ever found, TON 6-18 and Phoenix A, and we'll see what it really means for something to be that big, that dense, and that far beyond the kind of size we usually picture when we think of stars or planets or galaxies. These two black holes aren't just massive. They challenge the ordinary sense of scale we carry around. And while that might sound like the kind of thing that could keep you wide awake with questions, I promise we'll ease into it slowly enough that your mind can absorb everything without needing to hold on too tightly. Before we move any deeper into these distant giants, I'd love to know where you happen to be listening from tonight. Are you tucked under blankets, maybe with the lights dimmed and the room settled into that calm stillness that only happens once the day finally releases its grip? Or maybe you're listening on a couch somewhere, or in a chair, or even during a quiet moment before you fall asleep. Wherever you are, I hope it feels comfortable. It's always interesting to imagine people across so many places listening at the same moment, each of us with our own bit of sky outside, our own time of day or night, and our own small corner of the world. What time is it where you are right now? It feels fitting to ask that when we're about to talk about something as large and slow-moving as black holes, which don't really care about hours or minutes, or the schedules we follow every day. And if this helps you settle down, or gives you something soothing to lean your thoughts against, I'd be grateful if you'd like the video or subscribe. It helps this small space of quiet exploration reach others who might want something peaceful to end their day with. Nothing urgent, of course, just something gentle and supportive. So let's begin this slow walk toward two objects that sit so far from everyday experience that it's almost impossible to imagine them as real. But they are real. They're out there, shaping their surroundings in ways that defy simple comparison. TON 618 and Phoenix A. Two names that sound almost like characters from a story, but in truth they belong to some of the largest known black holes in the observable universe. One of them is so old and bright that we see it as it was billions of years ago, shining from a time when galaxies were just beginning to settle into their shapes. The other is buried deep within a galaxy cluster, sitting in the middle of a region filled with gas and stars that swirl around it with remarkable patience. Each of them gives us a chance to understand something about the limits of size and gravity, and how the universe builds structures so enormous that even our best comparisons can feel small. If you imagine a black hole at all, you might picture a dark sphere pulling in light and matter, with a gravity so strong that nothing can escape. That image isn't wrong, but with objects like TON 618 and Phoenix A, the idea of a black hole becomes something much larger. Their event horizons, the boundaries where escape becomes impossible, stretch across distances so wide that calling them wide doesn't really convey much. When you hear numbers like billions of solar masses, it's easy for the words to pass by without landing. Our minds aren't built to handle scales like that, so we'll approach it gradually. We don't need to rush into the math or the measurements, we'll just sink deeper into the idea one piece at a time. TON 618 sits in a part of the universe that is still glowing in its early stages when we observe it. Because of the speed of light and the distance involved, we aren't seeing TON 618 as it is today, we're seeing it as it was long ago, during a period when galaxies were actively forming and when supermassive black holes could feed on enormous amounts of gas around them, creating quasars that shone across billions of light years. TON 618 is the engine of one of those quasars. Even though the black hole itself is invisible, the matter spiraling around it becomes so hot and energetic that it produces incredible brightness. That brightness is one of the main reasons we can detect TON 618 at all. In a way, it announces itself just by eating, which is something black holes tend to do quite efficiently when the circumstances are right. Phoenix A, on the other hand, sits in a more mature part of the universe, not quite as ancient as the region where TON 618 appears. Phoenix A lies in the centre of the Phoenix cluster, a cluster of galaxies drawn together by gravity and filled with clouds of hot gas. At the centre of one of those galaxies is Phoenix A, a black hole massive enough to anchor the region around it. The environment is different from TON 618's early universe quasar setting. Phoenix A's surroundings are shaped by gas cooling, stars forming, and the steady influence that large black holes exert over enormous distances. While TON 618 blazes through time as something bright and energetic, Phoenix A sinks into its place as a slow, heavy presence in a crowded cosmic neighbourhood. But we're not comparing them yet. Before we do that, it's helpful to understand what it means for either of them to be considered large. Even our own Milky Way has a central black hole that we think of as pretty massive, and yet next to these two giants, it's closer to a lightweight. Sagittarius A, the black hole at the centre of our galaxy, contains around 4 million solar masses. That sounds enormous until you consider that Phoenix A is hundreds of times more massive, and TON 618 is thousands of times heavier still. It's an increase that doesn't just double or triple or grow in some comfortable familiar way. It leaps. It scales upwards so drastically that the numbers no longer reflect anything we've personally seen or touched. It's one thing to imagine a star with mass. It's another thing entirely to imagine millions of stars combined into one object, and then billions, and then more. TON 618 and Phoenix. They sit in that territory, where the gravitational pull is so strong and the size so extreme that even light becomes a trapped participant in the structure. Their growth depends on the material around them. TON 618 likely grew during a period in the universe when black holes could gather enormous amounts of matter, because the regions were rich, dense, and dynamic. Phoenix A, by contrast, seems to have grown in a quieter but still substantial environment, gradually pulling in material from the cluster around it over immense spans of time. Thinking about all this can feel overwhelming if you try to grasp it in one sudden leap. Instead, it helps to imagine these objects the way we might imagine distant mountain ranges. You don't need to define every ridge or measure every slope to understand that the mountains are large. You only need to take in the sense of their presence. TON 618 and Phoenix each have a presence in the universe. TON 618 is distant, ancient, visible, not because the black hole itself shines, but because the material orbiting it does. Phoenix A is deep within a cluster, influencing its environment through gravity in a slower, steadier manner. They exist in different parts of the cosmos and different periods of cosmic history, yet they share one trait. They challenge our understanding of size. This isn't the kind of comparison that needs to be rushed. We'll take our time and let each piece settle. The numbers will make more sense if we ease into them. Their distances, their masses, their environments, their ages. Each of these details helps form a clearer picture. And just as with anything large and unfamiliar, it's easier to absorb the information gradually, rather than trying to hold the entire concept in your mind at once. So we'll continue in a steady way, letting the scale of these objects open up gently. The comparison between TON 618 and Phoenix A isn't about declaring a winner. It's about understanding what size means in cosmic terms, and as we continue, everything will tie together in a way that makes these distant giants feel less abstract and more like real structures that exist in a universe we are part of. When you start thinking about black holes on the scale of TON 618 or Phoenix A, it helps to begin by grounding the idea of a black hole in something familiar, before stretching it into something far larger than ordinary examples ever prepare us for. Most people hear the term and picture a dark sphere pulling everything inward, a sort of cosmic drain where matter disappears. While that image is partly accurate, it's only a starting point. A black hole isn't really a hole or a sphere in the simple sense. It's a region in space defined by gravity strong enough that nothing inside a certain boundary can escape, not even light. That boundary is what matters most when we talk about size. It's called the event horizon, and its radius sets the scale for what we mean by big or small in the context of black holes. For the kinds of black holes found when stars collapse, the ones with masses a few times that of our Sun, the event horizons are relatively small compared to the distances between objects in space. They might span tens of kilometers, maybe a bit more. That scale is impressive if you imagine all that mass packed into such a tiny region, but it still feels manageable compared to the broader universe. But when black holes accumulate large amounts of matter over long periods of time, gas, dust, stars, sometimes even other black holes, the event horizon expands. And it doesn't just expand gradually, it grows according to mass, and mass can grow dramatically depending on the environment. A stellar black hole might be the size of a town or small city. A supermassive black hole like the one in the centre of the Milky Way is more like the size of a planetary orbit. That shift alone feels steep. Going from a few dozen kilometres to a region the size of Mercury's orbit shows how dramatically black holes can scale. But even then, we're still not close to the territory occupied by TON 618 or Phoenix A. Those two sit in a category that stretches so far beyond typical examples that the word supermassive starts to feel narrow. These are not simply black holes at the centres of large galaxies. They are black holes that define their entire regions, shaping the behaviour of everything around them on massive, sometimes cluster-wide scales. To understand why these black holes become so large, it helps to imagine their growth not as a sudden leap, but as a long, steady process spanning millions or billions of years. A black hole grows by pulling matter inward, but matter doesn't simply fall straight in. It forms a rotating disk around the black hole, because the gas and dust have angular momentum. This disk heats up as the material spirals closer, reaching temperatures so high that it emits radiation. When that radiation is intense enough, the black hole becomes visible as a quasar. TON 618 is one of these. It shines brightly because the gas near its event horizon produces extraordinary amounts of light as it moves through the disk. Phoenix A grows more quietly because it sits inside a galaxy cluster, where gas can settle toward the centre over long time scales. The cluster environment provides a reservoir of material, though the growth rate is shaped by many factors: the cooling of the gas, the structure of the galaxy cluster, and feedback processes that can either slow or enhance the accumulation of mass. Even though Phoenix A doesn't shine as a quasar in the way TON 618 does, its growth can still be significant. The black hole slowly captures gas, or merges with other black holes when galaxies collide inside the cluster. Over long enough periods, those processes add up. It's this accumulation, performed over immense stretches of time, that allows certain black holes to reach truly colossal sizes. The event horizons of these giants no longer resemble anything compact. They stretch outward into structures that could swallow solar systems many times over. To picture what it means for a black hole to be that large, think of the distance from the Sun to Pluto. That enormous span, one that takes spacecraft years to cross, is still tiny compared to the event horizons we're describing here. Some of the largest known black holes extend far beyond even that distance, and while we might try to imagine such a boundary in simple geometric terms, a region that big isn't something we can grasp intuitively. It becomes a matter of acknowledging size rather than truly picturing it. What makes TON 618 particularly noteworthy is that it reached its enormous size during an early part of the universe's history. When we observe it, we're seeing it as it was roughly 10 billion years ago. The universe then was dense with gas and full of opportunities for black holes to feed efficiently. TON 618 appears to have taken full advantage of those conditions. It accumulated mass at a rate that might not be possible today. That rate allowed it to grow into one of the most massive black holes ever identified. Because the light from TON 618 has taken so long to reach us, we don't know exactly how large it is now. It could be even more massive, or its growth might have slowed. Either way, the fact that it reached such a size so early is one of the reasons it stands out. Phoenix A represents a different path to becoming colossal. It didn't need early universe density or quasar-level feeding. Instead, it grew by residing in a cluster where gravitational interactions bring galaxies together. When galaxies merge, their central black holes have a chance to merge as well. Over billions of years, a black hole can experience multiple mergers, each adding to its mass. On top of that, the hot gas in galaxy clusters can cool and sink toward the center, providing additional material for growth. Phoenix A's environment gives it access to a more stable supply of matter, compared to black holes in isolated galaxies. Black holes become colossal not just because they pull in matter, but because they do so in environments that continually support that growth. Without that support, a black hole remains relatively small. With it, it becomes something that can distort an entire region of space. The process itself is slow but relentless. Gas flows inward, stars drift too close, smaller black holes fall toward the center during mergers. Each contribution adds to the total mass, slowly expanding the event horizon. It's difficult to compare these processes to anything we experience directly. We're used to objects growing in ways that make sense to the human brain. Plants grow from seeds, animals grow from infants, even stars grow by gathering material from surrounding gas clouds. But black holes grow in a way that feels more like accumulation than development. There is no structure inside to fill. The event horizon isn't a physical surface, it's simply the boundary defined by gravity. When a black hole gains mass, that boundary expands. That expansion is the growth we talk about. The interior remains hidden, and the process is more about how space curves around the object than about any addition to a physical body. The transition from black holes of ordinary mass to ones on the scale of TON 618 and Phoenix A doesn't happen in a single step. It happens over many orders of magnitude. A stellar black hole might grow slightly by pulling in gas from a failing star or from a nearby companion. A larger black hole forms when galaxies merge. A larger one still forms when multiple mergers happen across clusters. By the time you reach the kinds of black holes that anchor massive galaxies or entire clusters, the masses increase not by 10 or 100 but by millions or billions. That kind of increase reshapes the space around the black hole so dramatically that even stars at great distances can be influenced. When discussing colossal black holes, another factor becomes important: the relationship between mass and radius. If you double the mass of a black hole, the radius does not double. It increases in direct proportion to mass. This means the event horizon of a billion solar mass black hole is 1,000 times the radius of a million solar mass black hole. When dealing with sizes as large as TON 618 or Phoenix A, this scaling becomes enormous. It's not unusual for the event horizon of such a black hole to extend far beyond the size of our solar system. In some cases, it can reach distances that take light many hours or even days to cross. That is what is meant by colossal. It's natural to wonder how something that large fits into the universe without disrupting everything. The answer lies in how space itself works. Most of a galaxy is empty space. Most of a galaxy cluster is empty space. Even though the largest black holes have huge event horizons, they still occupy a tiny fraction of their surroundings. Their influence stretches over great distances, but influence is not the same as physical size. A black hole can anchor a region without filling it. Its gravitational pull shapes orbits, guides the flow of gas, and influences mergers, but stars still orbit normally unless they come too close. As black holes become larger, their gravitational pull becomes significant even for objects far away. This influence helps stabilize the central regions of galaxies or clusters. Over time, the presence of a huge black hole can alter the distribution of nearby stars. It can slow the formation of new stars by heating surrounding gas. Or in some conditions, it can stimulate star formation by stirring gas clouds. The effect depends on the environment. TON 618's environment was active with gas and intense radiation. Phoenix A's environment is calmer but still dynamic in its own way. Both environments allow black holes to interact with their surroundings in ways that shape long-term evolution. A colossal black hole can also produce jets of material. These jets are not made by the black hole itself, but by the region around it. As gas moves through the disk and becomes energized, it can be launched outward at high speeds. Some jets extend for thousands of light years. They carry energy into the galaxy or cluster, influencing the gas and potentially altering star formation patterns. TON 618 likely produced jets during its active quasar phase. Phoenix A experiences feedback from the center of its galaxy, which helps regulate the cooling of gas around it. These processes connect the black hole to its environment in ways that go beyond simple gravity. These connections show how black holes become part of the larger structures they inhabit. When they grow large enough, they act as regulators for their surroundings. They shape how matter moves and how galaxies develop. Their mass becomes a defining element in determining how a region evolves. This is why we find the largest black holes in the centers of the most massive galaxies or clusters. Gravity draws mass inward over time. Central locations receive more mergers, and once a black hole becomes massive, it influences future growth simply by being in the right place at the right time. As we explore these giants more deeply, the term colossal begins to feel less like an exaggeration and more like an accurate description of their role. We aren't talking about objects that are simply large. We're talking about objects that redefine the boundaries of size, objects that anchor galaxies and clusters, objects that grow through processes that operate on scales far beyond anything we encounter in daily life, objects that have existed for billions of years, shaping and reshaping their surroundings in ways that are still unfolding even now. When people first hear the name TON 618, it doesn't sound like much more than a catalogue entry. Just a string of characters, easy to pass over, the way you might overlook the label on a distant street sign when you're driving through a new city. Yet behind that label sits something astonishing. TON 618 is one of those discoveries that gradually pulls you in the more you look at it. At first it feels distant, almost anonymous, but as you begin to understand what it represents, that quiet catalogue number starts carrying the weight of something far older, far brighter, and far larger than anything we usually imagine as a single object. TON 618 is not only immense, it's ancient. When we observe it, we're seeing light that has travelled for billions of years to arrive here, crossing vast stretches of space and time. The light reaching us now began its journey during an era when the universe was still young, still shaping itself, still full of raw material that helped black holes grow quickly. To meet TON 618, even just through the limited details we can gather from such a distance, is to meet a black hole that has lived through more cosmic history than entire galaxies around us. The first thing to know is that we're not seeing the black hole directly. We can't. No one can. What we see instead is the glow of the quasar that surrounds it, an enormous disk of superheated gas that orbits the black hole at speeds approaching the speed of light. This disk becomes so hot that it outshines entire galaxies, making the region visible even from more than 10 billion light-years away. That brightness gives TON 618 a presence that stands out sharply against the background of the universe. It is astonishing to think of something so far away still showing up on our detectors with such clarity. TON 618 was first discovered in the 1950s during surveys that weren't even searching for black holes. Astronomers were cataloguing blue stars and other bright points of light in the sky. One of those points was TON 618, which at the time didn't appear to be anything unusually large. We didn't yet understand what quasars were, and the idea of a black hole with billions of solar masses wasn't even part of the scientific vocabulary. Only later, with more observations and better understanding, did astronomers realize that TON 618 wasn't a star at all. It was something far stranger. Its light spectrum contained signatures that didn't match stellar behavior. Instead, the signatures revealed enormous redshift, showing that the object was incredibly far away and incredibly luminous for something at that distance. Once astronomers realized what they were looking at, the numbers began to unfold in a way that made TON 618 impossible to ignore. The quasar it powers was releasing a staggering amount of energy, enough to be visible across most of the observable universe, and the only engine capable of producing that kind of energy was a black hole with unimaginable mass feeding on a thick, rapidly rotating disk of gas. Estimates eventually placed the black hole at more than 60 billion solar masses, and possibly much higher. That number isn't just large, it's a category all its own. Most black holes found in galactic centres are nowhere near that size. They might have millions of solar masses, some have a few billion, but crossing the threshold into tens of billions is rare. Ton 618 sits near the top of that range. When you think about what a solar mass represents, it becomes easier to appreciate why Ton 618 feels out of scale. One solar mass is the mass of our Sun. Our Sun contains more than 99% of the mass of the entire solar system. Multiply that by billions, and you're moving into territory where the numbers stop relating to anything familiar. If you try to compare the mass of Ton 618 to the mass of the Milky Way, you might find that the black hole outweighs the mass of all the stars in some smaller galaxies entirely. It becomes something so heavy that the space around it bends sharply. The curvature of space-time near the event horizon becomes severe enough that light can no longer escape. That boundary stretches across such a large distance that if Ton 618 replaced the centre of our solar system, the event horizon would reach far beyond the orbit of Neptune, and possibly even farther depending on the mass estimates used. But even these comparisons can only go so far. The numbers involved aren't meant to be taken as something we can visualise. They exist to anchor our understanding, to give us some framework for discussing a size that sits well beyond everyday intuition. Ton 618's mass isn't simply a statistic, it's a story about the early universe. To reach that size, Ton 618 had to grow at a remarkable rate. Growth for black holes is not a matter of gaining a little here and there. It requires an environment rich with gas and other material. The early universe provided those ingredients. Galaxies were colliding more frequently. Gas clouds were denser. Magnetic fields were different. The cosmic structures were still forming. Under such conditions, a black hole with the right location and conditions could grow rapidly. The light from Ton 618 comes from a time when galaxies were bright and turbulent, full of newborn stars and energetic processes. The black hole powering the quasar was probably feeding at close to the maximum rate allowed by the physics of accretion. That rate, known as the Eddington limit, describes the balance between gravity pulling material inward and radiation pressure pushing outward. Ton 618's luminosity suggests it was accreting material near that limit for long periods. If it maintained that pace even intermittently over hundreds of millions of years, it could have reached enormous mass before the universe settled into the calmer structure we see today. As the universe expanded and cooled, opportunities for such rapid growth became less frequent. That's one reason Ton 618 stands out. It represents a period of intense cosmic activity that is no longer typical. The fact that we can still see it now means the light travelled across a vast amount of space, unchanged except for stretching into redder wavelengths due to cosmic expansion. When that light leaves the quasar disk, the universe around it is young. Whole clusters of galaxies we know today haven't formed yet. Stars that will someday create planetary systems have not been born. The Milky Way itself is in a much earlier stage. Ton 618 exists at a point where cosmic evolution is happening quickly, and observing it gives us a look back into that time. There's something compelling about knowing that an object so distant and so old can still influence our understanding of black holes today. Even with modern telescopes and simulations, Ton 618 remains one of the most massive black holes known. Every time astronomers revisit the data, they refine the mass measurements and examine the quasar's behaviour. The spectrum of the light provides details about the gas in the accretion disk, revealing temperatures, velocities, and chemical signatures. From those clues, scientists infer the forces at play near the event horizon. These observations help test models of black hole growth, disk physics, and the conditions in the early universe. TON 618 becomes not only an object of fascination, but also a useful benchmark. Meeting TON 618 through these observations means accepting that much of what makes it impressive lies in distances and timescales that don't align with anything in daily experience. When we look at it, we're not looking at what it is now, we're looking at what it was billions of years ago. TON 618 might have continued to grow. It might have exhausted its surrounding gas. It might have gone through phases of increased or decreased activity. We don't know. We're seeing the version of TON 618 that happened to send photons in our direction at a time when dinosaurs hadn't yet walked the Earth, and the continents we know now didn't exist in their current forms. Some of the light from TON 618 began travelling long before our solar system even existed. Imagine that for a moment. Long before the sun formed, before planets gathered, before the Earth cooled, before any form of life began, the light you would eventually see in a modern telescope was already on its way. For billions of years, that light crossed empty space. It moved through regions that would someday become galaxies. It moved past clouds that would collapse into stars. It moved across the dark places where nothing yet existed. And then, eventually, it arrived here. Observing TON 618 becomes a reminder of the immense scale of time in the universe. The quasar powered by TON 618 is also an example of how black holes, despite their name and reputation for darkness, create some of the brightest phenomena in the cosmos. The accretion disk emits more light than ordinary stars because the gravitational energy converted into heat near the event horizon is so enormous. This brightness doesn't last forever. Eventually the gas supply diminishes and the quasar fades. TON 618 may no longer be as bright now as it appears in the light we observe. It might be a quieter black hole, sitting at the centre of a galaxy that has changed dramatically since those early days. The fact that we can only observe it through ancient light adds a layer of mystery to its current state. Even though we can't see TON 618 directly, the quasar surrounding it reveals enough detail to make a clear impression. The broad emission lines in its spectrum show gas moving at incredibly high speeds. Those lines spread out because the gas rotates rapidly. The shape and width of those spectral lines help estimate the mass of the black hole. This method isn't perfect, but it's the best tool available for black holes at such extreme distances. The numbers these analyses produce consistently place TON 618 among the most massive black holes ever measured. Thinking about TON 618 as a real object means accepting that it isn't just a distant point of light. It's a structure with scale, with history, and with a physical influence on its region of the universe. The galaxy surrounding TON 618 would have been shaped by the quasar's radiation. The gas in that galaxy would have been heated and stirred. Star formation might have been suppressed or triggered in certain regions depending on the energy flow. The black hole existed as a central anchor, guiding the evolution of the galaxy around it. Even though we can't see the galaxy clearly, the quasar gives enough hints to suggest that it was large and dynamic. Meeting TON 618 is also about recognizing its role as a marker for the early growth of black holes. The existence of such a massive black hole so early after the Big Bang challenges models of black hole formation. It forces scientists to consider how black holes could grow so quickly. Did they start from massive seed black holes formed from the collapse of huge gas clouds? Did they form from clusters of stars collapsing together? Or did they grow from smaller black holes feeding at rates close to theoretical limits? TON 618 sits at the centre of these questions because its existence demands an explanation. It is not a typical example. It's one of the extremes that push models to adapt. The name itself might seem simple, but once you explore the details, TON 618 becomes an object with layers. It's not just a measurement. It's a point in cosmic history, a powerful engine, a relic of a younger universe, and a signpost that marks the outer edge of what we know black holes can become. It sits far beyond anything our galaxy contains. Meeting it means stepping into a part of the universe where scale becomes something measured not in familiar units, but in broad comparisons meant to bridge a gap between what we know and what we can only understand through observation. Compared to the distant ancient glare of Ton 618, meeting Phoenix A feels like walking into a different kind of story. Instead of reaching back toward the early universe and catching the glow of a quasar that burned fiercely long ago, you shift toward a more settled part of cosmic history. You're not looking at the universe in its youth, you're looking at something that formed later, developed gradually, and lives in a quieter neighbourhood, at least by cosmic standards. Phoenix A sits at the heart of a galaxy cluster known as the Phoenix Cluster, a place filled with galaxies, gas, dark matter, and long, slow gravitational interactions that span hundreds of millions of years. This environment shapes Phoenix A in ways that make it distinct, almost like meeting someone who grew up in a busy city after meeting someone who grew up in a wild, chaotic landscape. The influences are different, the growth patterns are different, and the final result is something that carries those differences in its structure. Phoenix A didn't announce itself to us with the overwhelming brightness of a quasar. There was no blinding disk of radiation screaming across billions of light years. Instead, it sat quietly, hidden beneath layers of hot gas. Its environment is what first drew attention, not the black hole itself. The Phoenix cluster is unusually active in the sense that it contains enormous amounts of gas cooling rapidly, forming stars at a pace far higher than what's typical in most modern clusters. This intense cooling and star formation made astronomers curious. They pointed their telescopes toward the cluster, studied its structure, and gradually realized that at the center of all this activity was a galaxy with a black hole far larger than expected. That black hole became known as Phoenix A. What makes Phoenix A noteworthy isn't just its mass, although its mass alone places it among the largest black holes known. It's the environment it inhabits. Unlike Ton 618, which reached enormous size through rapid feeding in a dense early universe, Phoenix A grew through long-term interactions inside a cluster. That difference tells a story. In clusters, galaxies fall toward the center over time. They drift inward, pulled by gravity, and sometimes collide or merge. When galaxies merge, their central black holes can eventually sink toward each other and combine. Over billions of years, a black hole at the center of a cluster can gather mass through multiple mergers, each adding to its total. Phoenix A's presence at the center of the cluster made it the natural endpoint for many of those mergers, which allowed it to grow beyond what is typically seen in isolated galaxies. The Phoenix cluster itself gained attention because of the remarkable amount of gas cooling at its core. Most galaxy clusters have hot gas that remains stable, because the central black hole releases enough energy to keep it from cooling too quickly. Phoenix A, however, appears to be in a state where the energy feedback from its central black hole cycles through phases. During the times when the black hole is quieter, gas can cool and sink inward, forming new stars at a rate that is unusually high for a galaxy cluster. That cooling also provides material that the black hole can feed on, allowing it to grow further. Observations reveal that Phoenix A's black hole has a mass that rivals or surpasses even some of the most well-known giant black holes. Estimates place it at tens of billions of solar masses, though exact measurements vary depending on the methods used. While it may not reach the extreme values associated with Ton 618, Phoenix A falls into a category where large stops being a useful word. Once a black hole crosses into the billions of solar masses, it becomes something with a gravitational presence strong enough to influence an entire region of space for millions of light years in every direction. The galaxy that hosts Phoenix A isn't just shaped by the black hole. It exists in a state where the black hole helps regulate the flow of matter, the cooling of gas, and the formation of stars. When we talk about Phoenix A, we're talking about something that grew up in a crowded environment. The cluster around it contains hundreds of galaxies, each with its own history, its own stars, its own dark matter halo. Over immense spans of time, those galaxies interact. Some pass by each other, some merge, some transfer gas or stars. Phoenix A's galaxy sits in the center, like a gravitational anchor. It is the largest galaxy in the cluster, and the central position gives it advantages that black holes in smaller galaxies don't have. During mergers, the central galaxy tends to gather more mass. When gas cools in the cluster, much of it settles toward the center. That continual funneling of material toward the heart of the cluster feeds Phoenix A over time. Understanding Phoenix A means understanding how galaxy clusters work. A typical cluster contains gas heated to tens of millions of degrees. This gas emits X-rays, and the Phoenix cluster emits them at a level that initially puzzled astronomers. The gas was cooling faster than expected, cooling so quickly that it threatened to collapse inward and form stars at an extraordinary rate. Something in the center had to be influencing this process. That something was Phoenix A's black hole. As material falls toward a black hole, it can heat up and release energy. That energy spreads through the surrounding gas, preventing it from cooling too rapidly. But the Phoenix cluster seemed to be in a phase where the balance was off. Gas was cooling faster than the black hole could heat it, at least during certain periods. This imbalance offers clues to Phoenix A's behavior. It suggests that the black hole goes through cycles of activity. During quieter periods, gas cools, flows inward, and fuels star formation. That same inflow eventually feeds the black hole. As the black hole consumes material, it becomes more active, releasing bursts of energy that push back against the cooling gas. These cycles create an ebb and flow that shapes the cluster's core. Phoenix A's mass results from countless cycles like this, spread across hundreds of millions of years. The environment doesn't produce the immediate, intense feeding that creates a quasar like TON 618, but it offers a steady supply of material that accumulates gradually. Meeting Phoenix means recognizing that black holes grow not only through dramatic events but also through quiet ones. For every powerful burst of energy from accretion, there are long periods where the black hole grows slowly by drawing in gas or merging with smaller companions. The calm, steady environment allows the black hole to increase its mass over timescales so long they're difficult to imagine. If you think about how long 1 billion years is, and then imagine that growth happening over several billion years, you begin to understand how Phoenix A reached its current state. Another aspect of Phoenix A that stands out is the role it plays in regulating the cluster. When a black hole becomes large enough, it influences not just its host galaxy, but the entire surrounding environment. In the Phoenix cluster, the black hole's energy output shapes the rate of cooling, star formation, and gas movement. Without that influence, the cluster would look very different. The balance between cooling gas and black hole heating creates a system where star formation can surge during cooler periods, then slow down when the black hole heats the gas again. Phoenix A sits at the heart of these processes. Its presence is not passive. It actively contributes to the cluster's structure and evolution. Observations of Phoenix A have revealed features associated with active black holes. Cavities appear in the hot gas around the galaxy's center, voids where jets or outflows from the black hole pushed material aside. These cavities act as markers of past activity. They show where energy has been injected into the surrounding environment. The size and shape of these cavities help astronomers estimate how powerful the black hole's outbursts have been. Phoenix A's cavities indicate significant activity, though the black hole does not appear to be in its most active phase right now based on the light we observe. When astronomers consider the mass of Phoenix A, they use multiple lines of evidence. They observe the motion of stars close to the black hole. They measure the distribution of gas. They examine the X-ray emission from the cluster. These combined observations help approximate how much mass is required to produce the gravitational effect seen. The exact number varies depending on the models used, but the consistent result is that Phoenix A belongs to the uppermost category of black holes. It's a heavyweight by any measure, large enough to stretch its event horizon across distances that dwarf planetary orbits. What makes Phoenix A's mass intriguing is how different its growth likely was compared to TON 618. TON 618 grew rapidly when the universe was young. Phoenix A grew slowly in a mature universe where gas is less plentiful, and where most galaxies have already passed through their most active stages. That difference shows the diversity of ways black holes can reach enormous sizes. It also shows that the location of a black hole matters just as much as the timing. TON 618 had the advantage of forming early in a gas-rich environment. Phoenix A had the advantage of forming at the centre of a galaxy cluster, where material naturally drifts inward over time. They are two examples of the same phenomenon expressed under different conditions, but Phoenix A in particular demonstrates how black holes can remain influential long after the universe's most active period. Phoenix A doesn't shine with the dramatic brightness of a quasar. It doesn't reveal itself through the intense radiation associated with rapid accretion. Instead, it sits at the centre of a system where slow but steady processes build mass and shape the surroundings. Another reason Phoenix A stands out is the way it interacts with the cooling gas around it. The Phoenix cluster has one of the highest cooling rates of any known cluster. That means gas is losing heat quickly enough to form stars at a rapid pace. This cooling is partly offset by feedback from Phoenix A, but not completely. This imbalance is part of what makes the cluster so interesting. It represents a rare situation where the central black hole may not be injecting enough energy to fully regulate its environment. That imbalance allows star formation to proceed at a rate far above what is typically seen in cluster environments. For scientists studying the relationship between black holes and their surroundings, Phoenix A provides a valuable example. It shows how black holes and their clusters can influence each other in complex ways. It challenges assumptions about how much energy is needed to balance cooling. It helps refine models of cluster evolution, and it gives us a chance to see a system where the central black hole is both incredibly massive and still deeply connected to the flow of gas and stars around it. Meeting Phoenix A means accepting that not all giants announce themselves loudly. Some grow quietly, hidden behind layers of hot gas. Some accumulate mass not through dramatic bursts of activity but through long, steady processes, and yet the final outcome can match or approach the extremes produced by the early universe. Phoenix A is an example of slow, persistent growth building something that rivals the result of rapid, early feeding. Understanding how black holes grow means stepping into a process that unfolds slowly, steadily, and with a kind of patience that the universe itself seems comfortable with. Unlike stars or planets, which have clear physical sizes and surfaces, black holes expand through the accumulation of mass that falls toward them. Their growth is defined by gravity and the behaviour of the material around them, not by visible structures we can observe directly. When we talk about how they grow until they begin reshaping their own environments, we're really talking about the way matter behaves under extreme conditions and how long-term interactions create changes far greater than the individual steps that produce them. The earliest seeds of black holes form in a few different ways, and these origins shape their initial potential for growth. Some begin with the collapse of massive stars at the end of their lives. These stellar black holes are small compared to the giants we've been discussing. They might contain a few solar masses, or a few dozen at most. Others may form from the direct collapse of enormous clouds of gas early in the universe's history. These direct collapse black holes start out far larger, giving them a head start in environments rich with material. Some might even form from the collapse of extremely massive stars that existed only in the earliest generations of the universe. Whatever their beginnings, their growth depends on the availability of matter around them. When a black hole encounters gas, dust, or other material, the matter rarely falls straight into the event horizon. Instead, it orbits the black hole, flattening into a disk due to angular momentum. This disk is called an accretion disk. As gas particles in the disk collide with each other, they heat up. The friction and compression create temperatures so high that the disk emits intense radiation. This emission can be powerful enough to outshine entire galaxies if the black hole is feeding rapidly. That brightness is what allows us to see quasars, including the one powered by Ton-618. The accretion disk doesn't last forever. It depends on the availability of surrounding gas, but while it lasts, it becomes the main engine of black hole growth. Growth through accretion follows certain physical limits. One of the most important is the Eddington limit, which defines how much material a black hole can consume at a given time, before the radiation it produces pushes material away faster than gravity can pull it inward. If a black hole grows too quickly, the radiation pressure builds up and pushes back against the inflowing gas, reducing the accretion rate. This balance creates a kind of natural speed limit on growth. But in regions with dense gas, even growth at the Eddington limit can produce enormous mass increases over millions of years. Imagine a black hole feeding steadily for tens or hundreds of millions of years in a region where gas continues to flow inward. Even if the black hole grows at the maximum allowed rate, the amount of mass it accumulates becomes significant. Over these long stretches of time, the black hole expands its event horizon outward. The space around it becomes increasingly dominated by its gravitational influence. Stars closer to the center of the region gradually shift their orbits. Gas clouds stretch and compress as they fall toward the center. The growing black hole becomes a defining element of the galaxy's core. Another way black holes grow is through mergers. When galaxies interact or collide, their central black holes gradually fall toward each other. At first, they orbit at large distances, but over time, the emission of gravitational waves causes them to draw together. Eventually, they merge into a single, larger black hole. This process, although incredibly slow compared to human timescales, adds significant mass. In clusters where galaxy mergers are frequent, central black holes can grow substantially through this mechanism. Phoenix A is an example of a black hole whose growth has been shaped by mergers across long stretches of time. The galaxy sits at the center of a cluster where galaxies fall inward due to gravity. Each galaxy has its own central black hole, and many of those black holes eventually merge with the one at the center. These mergers don't produce the bright display associated with accretion. They add mass quietly, but their contribution can be enormous. Over billions of years, this slow, steady addition of mass helps create a giant like Phoenix A. Accretion and mergers often work together. A black hole that grows through mergers might find itself surrounded by leftover gas from the interacting galaxies, providing new material to feed on. Similarly, a black hole with an active accretion disk might help pull satellite galaxies inward, increasing the likelihood of future mergers. The processes reinforce each other, creating a feedback cycle that becomes increasingly influential as the black hole becomes larger. As black holes accumulate mass, their gravitational pull extends farther outward. While their event horizons mark the boundary beyond which nothing can escape, their gravitational influence stretches much farther. Stars that orbit near the growing black hole experience changes in their paths. Gas clouds find their motion altered. The black hole becomes the central anchor of its region. In a galaxy cluster, the influence extends to the surrounding hot gas. This gas is held in place by the collective gravity of the cluster, but the central black hole plays a key role in how that gas cools, heats, and moves. The growth of a black hole also affects the accretion disk itself. As mass increases, the gravitational potential increases. Gas falls inward faster, heating up more intensely, producing more radiation. During periods of rapid growth, the accretion disk can produce jets, streams of material accelerated to near light speed and launched perpendicular to the disk. These jets can stretch thousands of light years. They don't come from the black hole itself, but from magnetic fields and processes near the event horizon. The jets carry energy away from the center, heating the surrounding gas and influencing the environment far beyond the black hole. These jets, along with the radiation from the accretion disk, participate in what astronomers call feedback. Feedback refers to the way a black hole influences its environment through energy output. For example, when gas in a galaxy cluster cools too quickly and starts to flow inward, the black hole may begin feeding more rapidly. The increased accretion produces jets and radiation that heat the gas, slowing the cooling. This prevents gas from collapsing and forming too many stars. In some clusters, this balance is stable. In others, like the Phoenix cluster, the balance shifts. Phoenix A's feedback isn't always strong enough to counteract the rapid cooling of the cluster's gas, which allows the central galaxy to form stars at a rate that's unusually high. Understanding how black holes grow also means understanding the limits of growth. Eventually, the supply of material around a black hole can diminish. Gas might be consumed or blown outward. Nearby stars might stabilize in orbits that keep them at a safe distance. In isolated galaxies, this often happens once the black hole has used up the densest material in its surroundings. Growth slows, and the black hole enters a quieter phase. But in clusters, where material continues to drift inward over long periods, growth can persist. Phoenix A is an example of this continued growth. TON 618 represents the other extreme. It grew rapidly in a universe where gas was abundant. The early cosmic environment allowed quasars to shine brightly. The black hole consumed enormous amounts of material before the universe expanded enough to thin out the gas supply. TON 618 may have gone through phases of extreme brightness, during which its accretion disk released energy that affected its host galaxy. As gas heated and cooled, the galaxy's structure changed. The black hole shaped the evolution of its surroundings not through subtle cycles, but through powerful bursts of radiation. When black holes grow large enough, they reshape their neighborhoods in ways that go far beyond gravitational pull. They regulate the flow of gas in galaxies. They determine where stars can form and where gas will remain too hot. They create cavities in clusters by pushing gas outward through jets. They produce shock waves that ripple across vast distances. These effects aren't visible in the sense that we can see them directly, but they show up in measurements of temperature, density, and motion. And astronomers analyze the shapes and structures of X-ray emitting gas in clusters to determine where energy was injected. They study the motions of stars to see how their orbits have been altered. They examine the spectra of galaxies to detect changes caused by the central black hole's influence. Black holes also grow by capturing stars that wander too close. When a star approaches the event horizon, tidal forces can tear it apart. The debris forms a temporary accretion disk, producing a burst of radiation as it falls inward. These events, known as tidal disruption events, contribute small amounts of mass compared to mergers or long-term accretion, but they still matter. Over immense timescales, many small contributions add up. A growing black hole can also capture dark matter, though the process is less efficient than capturing ordinary matter. Dark matter doesn't interact through electromagnetic forces, so it doesn't form accretion disks. It passes through the black hole's region unless gravitational interactions cause it to fall inward. This process is slow and contributes less mass than accretion, but in clusters rich with dark matter, it can still play a role over billions of years. As black holes grow, they influence the distribution of stars in their host galaxies. Near the center, stars move in orbits shaped by the deep gravitational well. If the black hole grows large enough, it can disrupt the orbits of stars farther out. In some galaxies, the central region becomes depleted of stars because the black hole's gravitational interactions scatter them outward. This creates a core where star density is lower than expected. Observations of such cores give astronomers clues about the history of black hole growth. The incredible thing about black holes is that, even though they don't have physical surfaces, their presence changes the structure of everything around them. They act as gravitational sinks, drawing matter inward. They act as energy sources, heating gas through accretion. They act as sculptors of galactic cores, guiding the distribution of stars. As their mass increases, their influence becomes broader. In a galaxy cluster, the central black hole becomes part of a larger cycle, where cooling gas flows inward, feeding the black hole, which releases energy, which alters the gas, and the cycle repeats. Phoenix A's cluster is an example of this cycle functioning in a way that still isn't completely understood. growth is not simply a matter of mass increasing, it's also about the way the environment adapts. When a black hole grows, the temperature of the surrounding gas can change, the pressure can change, the motion of gas clouds can shift. The black hole's jets can carve pathways through the medium. Stars forming in the region might experience changes in their birth environments. Over time, these effects accumulate. Whole galaxies shift their structures in response to the long-term presence of a massive black hole. Even the shape of the galaxy's central bulge, the distribution of stars, and the way gas rotates can reflect the growth history of the black hole. Astronomers use these signatures to piece together a black hole's history. They examine the bulge mass, the velocity dispersion of stars, the amount of hot gas in the region, and the level of activity in the accretion disk. Black holes don't grow in isolation. They grow within ecosystems of gas, stars, and dark matter. Their growth changes those ecosystems in ways that influence future growth. This feedback loop becomes more pronounced as the black hole becomes larger. By the time a black hole reaches billions of solar masses, it is no longer just a feature of the galaxy. It becomes a core element of the galaxy's identity. When you think about black holes, the first idea that normally comes to mind is darkness, a place where light disappears, a region from which nothing returns. It's a simple picture, almost intuitive once you imagine gravity becoming strong enough to pull everything inward. But the truth is more complicated. Black holes don't only take light, they can also be the reason light shines across enormous stretches of space. They hide illumination within their boundaries while creating brilliant displays outside them. The result is something that both steals light and reveals it. That dual nature is part of what makes black holes so fascinating, especially when you're looking at giants like TON 618 and Phoenix A. Light is drawn inward when it gets too close to the event horizon. That's the boundary where escape becomes impossible. But before light reaches that boundary, it can behave in ways that are both surprising and informative. Light from gas orbiting a black hole becomes part of the story we interpret when we try to understand how large the black hole is, how fast material is spinning around it, and how much matter is falling inward. The light produced by the accretion disk becomes the marker of a black hole's activity. Without that light, many distant black holes would remain invisible. TON 618, for example, would never have been discovered if not for its brilliant quasar. This light does not originate from inside the black hole. It comes from matter outside the event horizon, heated to extraordinary temperatures through compression, friction, and motion. As gas spirals inward, it releases gravitational potential energy in the form of heat and radiation. This process continues until the gas crosses the event horizon, and everything beyond that point disappears from view. The black hole itself gives no light, but the disk around it can be so bright that it becomes one of the most luminous objects in the universe. With TON 618, the quasar it powers shines across distances so enormous that the light arriving here began its journey when the universe was much younger. That light reveals the behavior of gas orbiting the black hole at speeds close to the speed of light. The broad emission lines in its spectrum show how fast the gas moves. The greater the spread of those lines, the faster the rotation. From those speeds, astronomers estimate the mass of the black hole. TON 618's spectrum displays extremely broad lines, which correlate with a black hole of enormous mass. Without those luminous indicators, we would have no way of knowing its size or nature. In the case of Phoenix A, the light we detect is different. The black hole is not currently powering a quasar, at least not at the level seen in TON 618. Phoenix A's activity is revealed through X-rays emitted by the hot gas in the cluster, and by the cavities carved in that gas by jets that once flowed from the region around the black hole. These signatures aren't as bright or dramatic as a quasar, but they still serve as crucial clues. They show where energy was released, how gas is moving, and how the black hole influences the environment. Even without a shining accretion disk, Phoenix A reveals itself indirectly. Light around black holes behaves differently depending on the angle at which we observe it. Some of the most striking effects come from gravitational lensing, where the curvature of space caused by the black hole bends paths of light from objects behind it. This lensing can create arcs, distortions, or multiple images of background stars or galaxies. Black holes act like natural lenses, magnifying distant sources. The distortion isn't always visible through everyday telescopes, especially when we're dealing with objects as distant as TORN 1618. But the principle applies even there. Light passing near the black hole bends sharply. That bending becomes part of the system's behaviour even if we can't resolve the distortions directly. This bending of light is one of the reasons black holes are often depicted as spheres surrounded by warped rings or arcs. When matter in the accretion disk emits radiation, that radiation travels outward, but the paths curve due to gravity. Some light that would otherwise move away from us bends across the top or bottom of the black hole. Some light orbits it briefly before escaping. The result can be a region with bright, distorted arcs of illumination. Images produced by simulations show this effect clearly. The first direct image of a black hole, released by the Event Horizon Telescope collaboration, displayed this ring. It offered a glimpse of how gravity bends light near the event horizon. Black holes also reveal themselves through jets. These jets appear when magnetic fields in the accretion disk channel some of the material away from the black hole at high speeds. The jets don't come from the black hole itself, but from regions just outside the event horizon, where magnetic fields and rotating plasma interact. They can stretch for thousands or even millions of light years, depending on the black hole and its environment. TON 618 likely produced powerful jets during its quasar phase. Those jets would have influenced the gas in its galaxy, pushing some material outward, slowing star formation in some regions while perhaps helping trigger it in others. In a cluster like the one hosting Phoenix A, jets play a different role. They transfer energy into the surrounding hot gas, preventing it from cooling too quickly. That energy injection creates cavities, shock waves, and temperature variations. Even when the black hole itself is not shining brightly, the effects of past jets remain visible. These signs show how the black hole revealed itself in earlier periods of activity. Phoenix A's cluster contains evidence of such episodes. The cavities visible in X-ray images are shaped by interactions between the jets and the gas. Without those jets, the gas would cool too quickly, form stars rapidly, and change the structure of the cluster. Phoenix A's influence helps maintain a balance, even if that balance is imperfect. Light also plays a role in understanding how black holes evolve. When gas falls toward the black hole, the radiation produced can push back against inflowing material. This radiation pressure influences the rate of accretion. For quasars like the one powered by TON 1618, the brightness reaches the Eddington limit or comes close to it. The Eddington limit is the point where the outward pressure of radiation balances the inward pull of gravity. If a quasar tries to exceed this limit, the radiation pushes material outward, slowing accretion. This mechanism ensures the growth rate doesn't become too extreme. It doesn't prevent a black hole from growing, but it guides how quickly growth occurs. This balance between radiation and gravity becomes part of the story behind how black holes shape their neighborhoods. The light they reveal can regulate how gas moves. If a quasar becomes too bright, the light heats nearby gas, pushes it away, and reduces the amount of material available for future growth. This self-regulating system helps explain why black holes don't grow infinitely fast. It also helps explain why some black holes, like TON 618, grew rapidly only during specific periods when conditions allowed high accretion rates. The light produced by accretion disks also helps scientists study chemical compositions of the gas. Emission lines in the spectrum reveal the presence of elements such as hydrogen, helium, carbon, nitrogen, or oxygen. These elements offer clues about the history of the galaxy hosting the black hole. For TON 618, the high redshift shifts these lines toward longer wavelengths, but the pattern still reveals important characteristics. It shows the galaxy was undergoing star formation and chemical enrichment even at that early time. This enrichment influenced the gas feeding the black hole. The observations helped scientists understand what early galaxies were like, how they evolved, and how their central black holes grew. In Phoenix A's cluster, the light revealed through X-rays provides information about the temperature, density, and metallicity of the gas. From these properties, scientists infer how long the gas has been cooling, how fast stars are forming, and how much energy the central black hole has injected into the region. Even though Phoenix A doesn't show the bright optical display of a quasar, it produces light in other wavelengths that are just as revealing. X-ray observations show where the gas has been heated. Radio observations show where jets have moved through the cluster. These different wavelengths create a layered picture of the environment. Light becomes a tool for studying the growth history of black holes. It becomes the means by which scientists measure motion, temperature, distance, and composition. The behavior of light near the black hole reveals the velocity of the gas. The redshift reveals the distance. The shape of the emission lines reveals the geometry of the accretion disk. The energy distribution reveals the temperature. The way light bends reveals the curvature of space. All of these clues help astronomers build a model of the black hole's properties, even though the black hole itself remains hidden. The dual nature of black holes stealing light and revealing it also appears in the concept of gravitational redshift. As light climbs out of the deep gravitational well near a black hole, it loses energy. The wavelength stretches, shifting toward the red end of the spectrum. This shift becomes more pronounced the closer the light originates to the event horizon. For quasars, some of the emitted light comes from regions very near the black hole, and gravitational redshift becomes part of the observed spectrum. This effect helps scientists determine how deep the gravitational well is, which in turn helps estimate the black hole's mass. Another form of light-related behavior occurs when gas falls inward and produces flares. These bright flares can last for minutes, hours, or days depending on the size of the black hole and the amount of material involved. The light curves of these flares, meaning the way brightness changes over time, reveal details about how gas interacts with magnetic fields and how turbulence develops in the disk. Even though TON 618 is too distant for us to observe such flares in detail, closer black holes show this behavior clearly. Scientists use these observations to model what might happen in quasars farther away. In the Phoenix cluster, the light we detect from the hot gas also reveals the velocity of the gas as it moves. Differences in temperature and density create structures that can be analysed to determine where the gas is flowing and how the black hole influences that flow. This information helps understand how the black hole regulates the environment. Without such observations, the cluster would be harder to interpret. The contrast between TON 618 and Phoenix A becomes clear when considering the light associated with each. TON 618 is a lighthouse from the early universe, a quasar so bright that its light crosses billions of years to reach us. Its illumination comes from intense feeding, dense gas, and a rapidly spinning disk. Phoenix A, by comparison, offers quieter forms of light, X-rays from hot gas and radio signatures from past jets. Both show the presence of a massive black hole, but through very different expressions. Even when black holes appear quiet, light reveals their history. Jets leave traces, cavities remain in gas, temperature gradients reflect past energy input. The stolen light, the light pulled inward and absorbed at the event horizon, leaves no direct signature. But the light created outside that boundary can tell an entire story. This balance between what disappears and what becomes visible defines how we understand black holes. They hide the final product but illuminate the journey. Trying to understand the weight of something like TON 618 or Phoenix A means stepping into territory that isn't built for ordinary intuition. Even the word weight becomes a fragile metaphor, because gravity in the context of black holes is not the simple pull we experience on Earth. Instead, it's the curvature of space caused by concentrations of mass so dense and so extreme that they force light, time, and matter into unfamiliar shapes. When astronomers talk about weighing a black hole, They're really talking about estimating how much mass is required to create the effects we observe. And when those estimates climb into the billions of solar masses, the numbers begin to lose connection with anything familiar. Still, understanding how we estimate that mass helps make the scale a little less remote, and it brings us one step closer to seeing these black holes not as incomprehensible abstractions, but as physical structures that obey rules we can measure. Mass measurements for black holes rely on indirect evidence. We never measure a black hole directly. We observe how the surrounding environment behaves and use those behaviors to infer the mass required to produce them. For nearby black holes like the one at the center of the Milky Way, this process is remarkably precise. Astronomers have tracked the motion of individual stars orbiting closely around it. Those stars move with such speed that only a massive black hole could keep them in orbit without flinging them outward. Their motion is predictable enough that we can calculate the black hole's mass to an impressive degree of accuracy. But for black holes as distant as TON 618 or as heavily obscured as Phoenix A, other methods are needed. One of the most common ways to estimate the mass of distant black holes is by examining the broad emission lines in the spectra produced by their accretion disks. When gas orbits a black hole, it moves at extraordinary speeds, especially when the black hole is large. The radiation emitted from this gas contains emission lines that become broadened, stretched out across a wider range of wavelengths. The amount of broadening correlates with the speed of the gas. Gas near a massive black hole moves faster than gas near a smaller one. By measuring those line widths, astronomers can calculate the orbital velocities. Once those velocities are known, they can be used to estimate the mass of the black hole. TON 618's broad emission lines are some of the widest ever observed. They tell a story of gas moving so rapidly that only a black hole with tens of billions of solar masses could hold it in orbit. That speed doesn't come from chaos. It comes from the black hole's gravitational pull. The faster the gas moves, the deeper the gravitational well must be. And the deeper the gravitational well, the more massive the black hole. The term solar mass is the standard unit for measuring these quantities. One solar mass is the mass of our Sun. It's a conveniently sized unit because stars are common and because the Sun's mass is familiar in astronomical terms. But when dealing with black holes as large as TON 618 or Phoenix A, solar masses stack up so quickly that the numbers no longer resemble anything we can picture. 1 million solar masses is already far beyond human experience. 1 billion solar masses is another level entirely. When astronomers say TON 618 has more than 60 billion solar masses, they're using a unit that is itself enormous, yet they're multiplying it tens of billions of times. To make sense of such numbers, people often compare black hole masses to the mass of galaxies. The Milky Way contains roughly 1 trillion solar masses if you include dark matter. But the stars themselves add up to only about 100 billion solar masses. TON 618's mass is comparable to a significant fraction of the Milky Way's total stellar mass. It exceeds the stellar mass of many entire galaxies. Phoenix A also occupies this upper range. Its mass, though not as extreme as TON 619's based on current measurements, remains among the largest recorded. Another way black hole masses become meaningful is by considering the size of their event horizons. The radius of the event horizon is directly proportional to mass. The more mass, the larger the radius. For a black hole with billions of solar masses, the event horizon can be so large that light takes hours or even days to cross from one side to the other. For TON 618, the event horizon could span distances comparable to the orbits of outer planets in our solar system. It becomes a region so large that imagining it as a sphere becomes difficult. Yet the only reason it's that large is because the mass is so immense. Phoenix A's event horizon also stretches across extraordinary distances, but its environment makes the mass estimate more complicated. Its mass comes from analysing the distribution of stars in the central galaxy, measuring the temperature and density of the cluster's gas, and observing how that gas moves. The gravitational influence of Phoenix A's black hole affects the cluster's core. The the hot gas emits X-rays, and the structure of that emission reveals how much mass must be present to hold the gas in place. These measurements, combined with other data, allow astronomers to estimate the black hole's mass. Estimating mass from X-ray emissions or cluster structure is not as straightforward as using emission lines in a quasar. It involves multiple models and assumptions. The mass of Phoenix A may evolve as observational techniques improve, but even with uncertainties, it clearly falls within the upper tier of supermassive black holes. It is a heavyweight in a region where galaxies collide, merge, exchange material, and funnel mass toward the center. The process of weighing black holes becomes more challenging at greater distances. The farther away a black hole is, the more its light is redshifted. Redshift makes spectral lines harder to interpret. Light stretches as the universe expands, shifting toward longer wavelengths. High redshift quasars like TON 618 are some of the most challenging objects to analyze. Yet with careful calibration, the broad emission lines still reveal enough information to estimate mass. A key part of weighing black holes involves the relationship between black hole mass and other properties of galaxies. In nearby galaxies, astronomers have discovered a strong correlation between the mass of the central black hole and the velocity dispersion of stars in the galaxy's bulge. This correlation, known as the M-sigma relation, shows that black hole mass and galaxy structure are deeply connected. Although the relationship becomes less reliable at extreme masses, it provides a general sense of scale. In more typical galaxies, if you measure how fast stars move in the central region, you can estimate the mass of the black hole, but for giants like Phoenix A, where the black hole mass is tens of billions of solar masses, the relationship becomes strained. These extreme black holes sit at the edges of what the M-sigma relation predicts, which is one reason they are so interesting. Mass estimates also rely on models of how gas interacts with the black hole's gravitational field. For quasars, the gas in the accretion disk emits radiation that reflects off surrounding structures, creating time delays between certain wavelengths. This technique, called reverberation mapping, helps determine the size of the gas region and, combined with the velocity of the gas, helps estimate the black hole's mass. Although TON 618 is too distant for detailed reverberation mapping, other quasars have been studied this way, and the relationships discovered from those studies help calibrate the mass estimates for objects like TON 618. The idea of weighing black holes by observing their environments is part of what makes them feel more real. Even though the interior of a black hole remains hidden, the behavior of the surrounding matter obeys predictable rules. We can calculate how fast gas should move near a certain mass. We can calculate how much X-ray emission should come from gas at a certain temperature. We can analyze the size of cavities carved by jets and estimate how much energy they required. All these measurements, when combined, form a picture of the black hole's mass. As black holes grow larger, these measurements reflect increasingly dramatic effects. Gas moves faster, radiation becomes more intense, cavities grow larger, event horizons expand. The gravitational pull stretches across larger distances. Stars near the center show stronger accelerations. The environment becomes more shaped by the black hole than by any other source. When a black hole reaches tens of billions of solar masses, its mass becomes comparable to the combined mass of millions or billions of stars. One way to think about the scale is to compare the gravitational pull of a black hole to the gravitational pull of a star. A star like the Sun pulls planets into stable orbits. A black hole with a few million solar masses pulls stars into tight, fast orbits. A black hole with tens of billions of solar masses pulls the entire central region of a galaxy or cluster into its gravitational influence. The effect stretches far beyond the event horizon. Even stars thousands of light years away can feel the impact of a giant like Phoenix A or TON 1618. The event horizon size offers another angle. For a black hole with one solar mass, the event horizon has a radius of about 3 kilometers. For a black hole with 60 billion solar masses, the radius becomes about 180 billion kilometers. That distance is so large it becomes difficult to express in familiar terms. It extends well beyond the orbit of Neptune, possibly far enough to engulf entire planetary systems if placed at the centre of them. This radius doesn't represent a physical surface, but it defines the region where escape becomes impossible. The larger the mass, the larger the event horizon. The idea that a single object could have such mass challenges ordinary intuition. The mass didn't appear all at once, it accumulated over billions of years, through steady feeding or through mergers. In the case of TON 618, fast feeding during the early universe allowed rapid growth. In the case of Phoenix A, long-term interactions in a cluster allowed slow accumulation. Both paths lead to objects with extreme mass. As mass increases, the black hole's gravitational signature becomes more pronounced. If you could map the gravitational field of a galaxy cluster, the strongest pull would come from the centre. That pull is one way astronomers estimate mass. The curvature of space affects how light moves through the region. Subtle distortions in the shapes of background galaxies reveal the presence of massive objects. This technique, known as gravitational lensing, helps estimate the mass of both clusters and the black holes within them. While gravitational lensing isn't precise enough to measure the mass of Phoenix A directly, it helps constrain the mass of the cluster, which in turn influences estimates of the black hole. Another technique involves analysing how gas cools in the cluster. The rate of cooling depends on the density and temperature of the gas. If the gas is cooling too quickly, there must be a powerful central source injecting energy into the region. The amount of energy required helps estimate the mass of the black hole. Phoenix A's cluster cools unusually quickly, which offers clues about the black hole's influence. The numbers associated with black hole mass become more meaningful when placed in a timeline. TON 618's mass was already tremendous billions of years ago. Phoenix A's mass accumulated gradually over billions of years. These time frames allow black holes to reach sizes that would be impossible in shorter periods. Even with modest feeding rates, billions of years are enough to accumulate staggering mass. As we move deeper into the comparison between these giants, it becomes clear that mass is not just a number. It becomes a key to understanding how each black hole grew, how it interacts with its surroundings, and how it fits into the structure of the universe. TON 618's mass tells a story of rapid early growth in a young universe. Phoenix A's mass tells a story of long-term development in a mature cluster. Each mass measurement represents a journey. Trying to compare something like TON 618 with something like Phoenix A is a little like trying to compare the height of a mountain to the depth of an ocean. They exist in the same universe, they follow the same physics, but the environments that shape them, the histories they reflect, and the ways they influence their surroundings make the comparison feel less like putting two objects side by side, and more like trying to bring together two different categories of existence. Even when their masses fall within similar ranges, the meaning of those masses changes depending on where the black hole grew, how it fed, and how long it had access to material. Numbers alone don't fully describe what they are, but numbers are where we can begin, and then move slowly into the more difficult space, where a direct comparison becomes something more nuanced. One of the first difficulties in comparing these giants comes from the environments they inhabit. TON 618 sits at such an extraordinary distance that we're seeing it through light that has travelled for more than 10 billion years. The environment around it during that time was nothing like the one Phoenix A experiences now. The early universe was dense, full of gas, and full of objects forming rapidly. Collisions between galaxies were more frequent. Star formation rates were higher. Gas clouds had not yet been depleted or stabilized. Everything about the early universe favored rapid growth for any black hole located in a region with access to abundant material. TON 618 is a product of that intense period, which makes its mass reflect not just gravitational pull, but the conditions of a universe still in its early stages of formation. Phoenix A occupies a different kind of neighbourhood. It lives in a galaxy cluster that has existed for billions of years. The gas around it is hot, thin, and stabilized by the collective gravity of the cluster. Its growth happens slowly, influenced by long-term galaxy mergers, cooling flows, and steady accretion. The cluster environment provided material, but not in the dramatic, turbulent way that early galaxies fed black holes. Instead, Phoenix A gained its mass over immense stretches of time, shaped by the quieter processes that dominate in the later universe. Even if the two black holes have comparable masses, the way they reach those masses cannot be placed on the same timeline or described through the same mechanisms. Another challenge in comparing these two giants lies in the limits of observation. TON 618 reveals itself through the brightness of its quasar. That brightness allows precise measurements of the gas orbiting around it, which in turn helps determine its mass. The quasar's light makes TON 618 relatively straightforward to study at certain wavelengths. Phoenix A, however, doesn't present itself with the same kind of illumination. Its accretion rate is lower. Its disk is not shining with the intensity of a quasar. Much of what we infer about Phoenix A comes from the behavior of the gas in the cluster around it, and from the structure of the galaxy at the cluster's center. The mass estimate depends on models of how the cluster behaves, and those models come with uncertainties. Even with careful analysis, Phoenix A's mass range is less direct than TON 618's. This difference in measurement technique matters when trying to compare the two. TON 618's mass is tied to the speed of gas in the accretion disk. Phoenix A's mass is tied to the motion of stars, the temperature of gas, and the gravitational structure of the cluster. Both methods are valid, but they describe different environments. They rely on different assumptions. They produce numbers that can be compared, but only with the understanding that the numbers reflect different physical processes. The next difficulty involves scale. Even though both black holes fall within the same general category of extreme supermassive black holes, their sizes create challenges for direct comparison. When dealing with objects that each contain tens of billions of solar masses, the differences between them become proportionally small. For example, if one black hole has 50 billion solar masses and another has 60 billion, the difference of 10 billion sounds enormous in everyday terms. But in the context of their overall scale, the difference becomes a fraction of their total. Comparing them becomes similar to comparing two skyscrapers that both reach well into the clouds. One might be taller than the other, but the comparison doesn't fully capture what it feels like to stand beside either one. This problem becomes more pronounced when thinking about event horizons. The radius of an event horizon scales directly with mass. But once you reach a certain scale, the radius becomes so large that the difference between two giants might be measured in distances that sound smaller than expected given their mass difference. If one event horizon extends beyond the orbit of Neptune, and the other extends even farther, both still exceed anything we experience directly. The fact that one is larger becomes interesting, but not necessarily meaningful in isolation. Even the way they influence their surroundings differs so much that direct comparisons lose clarity. TON 618 shaped its host galaxy through intense quasar activity. Its radiation influenced star formation. Its growth occurred during a time when galaxies were still assembling. Phoenix A influences its cluster in slower ways. It heats the surrounding gas through jets and outflows. It participates in cycles of cooling and heating. It helps regulate the star formation rate of the entire central galaxy. The environments they control are not the same. TON 618 shaped a young galaxy. Phoenix A shapes a mature cluster. One environment is dynamic and rapidly evolving, while the other is stable and massive. These differences raise the question of what we even mean when we say one black hole is bigger than another. If size refers only to mass, then yes, comparison is possible. But if size refers to influence, environment, history, or growth, the comparison becomes more complex. TON 618's influence extended across its host galaxy during a period when galaxies were changing dramatically. Phoenix A's influence extends across a cluster where cooling gas, hot plasma, and galaxy interactions operate on longer timescales. One is not simply bigger than the other. They are large in different contexts. Comparing their light is also challenging. TON 618's quasar is one of the brightest known. Phoenix A's black hole currently shines far less brightly. But brightness doesn't always reflect mass, it reflects feeding rate. A black hole that is not actively consuming large amounts of gas will appear dim even if its mass exceeds that of a brightly shining quasar. So comparing their light output is not a meaningful way to compare their size. It only tells us what they're doing right now, or rather, what they were doing when the light began travelling toward us. Another point of complexity involves time itself. TON 618 is observed as it was more than 10 billion years ago. If we could see it today, its mass might be different. It might have grown, it might have quieted, it might have changed in ways we cannot observe. But because of the speed of a light and the expansion of the universe, we can only see its ancient state. Phoenix A, on the other hand, is observed in a far more recent condition. Its environment is closer in time to our present day. Any comparison must account for this difference. We're not observing them in the same era. One is a snapshot of an early universe. The other is part of a contemporary cluster. This time, difference complicates the storytelling aspect of comparison. TON 618 grew during a period when black holes frequently reached sizes that seem improbable today. Phoenix A grew during a period when black holes tended to grow more slowly. The paths that lead to their current masses are shaped by cosmic history, not just by the physics of accretion. When comparing the two, we're comparing two epochs, two kinds of cosmic environments, and two very different growth stories. One of the few ways to compare them meaningfully involves thinking about the flow of matter. TON 618 consumed gas quickly, heated its surroundings intensely, and influenced the evolution of its galaxy rapidly. Phoenix A consumes gas slowly, influences cooling flows, and shapes its cluster through long-term cycles. Comparing these flows reveals differences in the mechanisms of mass accumulation. One grew from abundance and youth, the other grew from patience and structure. Even if we move into the realm of gravitational influence, the comparison becomes more complicated than it seems. The gravitational sphere of influence for a black hole depends on both its mass and the environment around it. TON 618's gravitational influence extended across the central region of its host galaxy. But its galaxy was young, and its gravitational relationships were more fluid. Phoenix A's gravitational influence interacts with the entire core of the cluster. The cluster's mass, temperature, and density all respond to the presence of the black hole. Comparing their gravitational influence is not just a matter of comparing the strength of their pull, it's a matter of comparing the structures they inhabit. Another layer of complexity emerges when considering how astronomers classify extreme black holes. TON 618 belongs to the category of hypermassive black holes, produced during the quasar era. Phoenix A belongs to the category of brightest cluster galaxies with central black holes shaped by mergers. These categories describe different evolutionary pathways. Comparing them becomes similar to comparing two animals from different ecosystems. They may have similar sizes, but their structures and lifestyles evolved under different pressures. Even when looking at their jets, which offer another hint of comparison, the differences persist. TON 618 likely produced strong jets during its quasar phase, affecting its host galaxy. Phoenix A's jets create cavities in the cluster, injecting energy into the environment. Both produce jets, but the scale of influence differs because of the density and temperature of the surrounding gas. Comparing jet size alone doesn't reflect their overall influence. A jet travelling through a young galaxy behaves differently from a jet travelling through cluster gas. One might attempt to compare them through energy output. TON 618's quasar emits enormous amounts of radiation. Phoenix A's energy output appears through heating of the cluster gas. Both represent immense power, but energy output depends on activity level, not mass. So comparing them through energy becomes misleading. Some people attempt comparisons through analogies. For example, they might say that if TON 618 were placed in the centre of the solar system, its event horizon would engulf certain planets. They might say the same of Phoenix A. But these analogies only highlight the general scale. They don't reveal meaningful differences beyond showing that both are far beyond ordinary comprehension. The deeper truth is that comparing these giants forces us to confront the limits of our own intuition. The numbers exceed anything we interact with. The environments differ dramatically. The histories diverge. The physical effects become more about large-scale structure and less about direct experiences. Even when we reduce everything to mass, the comparisons feel incomplete, yet comparing them still has value. It helps us understand the diversity of pathways leading to extreme mass. It helps us see how black holes evolve under different cosmic conditions. It helps illuminate the history of the universe. The comparison becomes not a matter of which is bigger, but a matter of what each represents. TON 618 represents an early era of rapid growth. Phoenix A represents a later era of slow accumulation. One shows what black holes could become when the universe was young and full of raw material. The other shows what black holes can become when time and gravity work together over billions of years. The attempt to compare these two giants inevitably leads to the next question, which is how the universe provided the environments necessary for such growth in the first place, and how early cosmological conditions shaped the birth of black holes capable of reaching these extremes. Stepping back into the quasar era begins with accepting that the universe we see today, with its long-cooled galaxy clusters and mature spirals, looked nothing like this during its youth. The early universe was shaped by conditions that favoured extremes. Everything unfolded more quickly. Matter gathered into structures much faster. Gas was denser. Temperatures were higher. The cosmic web was still forming. The laws of physics were the same, but the circumstances in which those laws acted produced results that we don't see as easily in the current universe. When you travel in your mind toward this era, even just conceptually, the differences begin to reveal why black holes like TON 618 were possible. They reflect not only gravity, but the environment of a time when the universe was far more turbulent than it is today. The quasar era is a period in the universe's history when supermassive black holes were feeding at extraordinary rates. They pulled in gas so efficiently that the accretion disks around them produced light bright enough to outshine entire galaxies. These quasars were not rare. They were relatively common during this time. The universe was only a few billion years old. Galaxies were compact and gas-rich. Star formation rates were high. Collisions between galaxies happened regularly. Interactions were intense, frequent, and full of consequences. A black hole placed inside one of these environments had access to reservoirs of matter that could sustain rapid feeding. Part of what made the quasar era possible was the availability of cold gas. Even though the universe was hotter overall, the gas inside galaxies could cool efficiently enough to collapse into dense clouds. These clouds were easily disrupted. When galaxies interacted, their gas could be funneled toward the center, feeding the black holes. This funneling effect often triggered starbursts. It also created the high accretion rates needed to produce quasars. TON 618's brightness, seen from more than 10 billion light-years away, reflects an environment with extraordinary fuel supply. Its quasar burned so intensely that the light travelled across the expanding universe and still reaches us with enough strength to be measured. Another piece of the quasar-era puzzle involves the early growth of black hole seeds. The earliest black holes formed relatively soon after the first stars. Some came from the collapse of those early massive stars. Others may have originated from the direct collapse of giant gas clouds, bypassing the stellar phase entirely. These initial black holes were larger than typical stellar remnants today. A black hole that begins life with thousands or even tens of thousands of solar masses has a strong advantage in a universe with abundant gas. With a head start and access to dense material, such a seed could grow rapidly, reaching millions of solar masses in relatively short periods of cosmic time. Once a black hole becomes large enough, the accretion disk around it becomes especially efficient at converting gravitational energy into radiation. This efficiency fuels the quasar phase. During the quasar era, Many black holes likely spent extended periods near the upper limit of accretion. That limit, determined by radiation pressure pushing outward against incoming gas, sets a natural cap on how quickly a black hole can grow. But even with that cap, the growth rate remains incredibly fast compared to later periods in cosmic history. Growing at the maximum sustainable rate, a black hole can double its mass in tens of millions of years. That timescale may seem long, but in the universe's early history it allowed black holes to reach enormous sizes quickly. The quasar era also coincided with frequent mergers between galaxies. When two galaxies collided, their stars often passed through each other without interacting directly, but their gas did not. Gas clouds collided, compressed, and funneled toward the centre. These inflows provided additional fuel for central black holes. Meanwhile, the black holes themselves gradually spiraled inward until they eventually merged. Each merger added mass. Each inflow of gas fed the accretion disk. The combined effect created black holes that grew through multiple channels at once. TON 618 likely formed in such an environment. The early universe provided everything it needed: dense gas, high merger rates, abundant fuel, and rapid cooling. The quasar phase it experienced would have illuminated its host galaxy during a time when galaxies were still assembling. The light we see today from TON 618 comes from this extraordinary period. It shows us a black hole growing at a pace that is difficult to replicate in today's calmer cosmic conditions. Understanding why quasars were so common requires looking at how galaxies formed at that time. Galaxies grew through both smooth accumulation of gas and through mergers. Every fresh supply of material created opportunities for black holes to feed. The universe had not yet expanded enough to thin out the gas between galaxies. The cosmic web was thick with filaments of matter connecting, forming galaxies. These filaments served as highways for gas to flow into galaxies. As that gas accumulated, it often travelled all the way to the centre, where the black hole waited. One of the remarkable things about the quasar era is that many of the most distant quasars we see today were already extremely massive by the time the universe was only a fraction of its current age. This creates what astronomers call the black hole growth problem, or more specifically, the question of how black holes could grow so large so quickly. TON 618 is one of the objects that pushes this question to its limits. Its mass, measured through the broad emission lines of its quasar, suggests that it had already achieved a size that would require efficient, sustained feeding. Several theories attempt to explain this rapid growth. Some suggest that the seeds of these black holes were unusually massive. Others suggest that accretion may not always be limited by the standard Eddington rates. Under certain conditions, gas could fall inward in a way that temporarily exceeded those limits. Another possibility involves the early formation of unusually dense gas structures that facilitated rapid feeding. The quasar era was full of environments that were unlike anything commonly found in the later universe. These environments allowed exceptional cases to emerge, cases like TON 618. Even understanding the brightness of quasars helps illuminate the nature of the early universe. Quasars are visible across enormous distances because they produce so much light. That light carries information about the gas near the black hole. The emission lines reveal temperatures and velocities. The redshift reveals distance and cosmic age. The absorption features caused by gas in the intervening universe reveal the distribution of matter along the path the light travelled. The quasar era therefore provides a kind of backlighting for the early universe, allowing astronomers to study the structure of cosmic gas. The quasar era was not uniform. It peaked at a time known as cosmic noon, a period when star formation and black hole growth reached their highest rates. After this peak, the universe continued to expand. Gas became more diffuse. Star formation rates began to decline. Galaxies evolved into more stable structures. The environment that allowed the formation of hypermassive black holes faded. Phoenix A grew during this later period, when the universe was older and calmer. Its growth depended more on mergers within its cluster than on the rapid feeding that defined the quasar era. This shift in cosmic conditions helps explain why black holes like TON 618 are more rare today. The early universe produced many quasars, but over time, the supply of easily available gas diminished. Galaxies consumed their gas reservoirs to form stars. Clusters stabilized their hot gas environments. The number of bright quasars declined dramatically. Most black holes today exist in quieter states. They feed slowly. Their accretion disks are faint. Their activity comes less from bright quasars and more from subtle interactions with the surrounding environment. Travelling conceptually through the quasar era requires imagining not only the behaviour of black holes, but the structure of the universe itself. At that time, the cosmic microwave background was warmer. The distance between forming galaxies was shorter. Dark matter halos were assembling. Filaments of gas and dark matter traced the structure of what would become the large-scale architecture of the universe. These filaments were thicker and more efficient at channeling gas into galaxies. Every galaxy had access to material that could flow toward the centre. Black hole growth during the quasar era also influenced galaxy evolution. When a quasar became active, it could heat gas, push it outward, and suppress star formation. This feedback mechanism shaped the development of galaxies. Some galaxies grew large because their black holes were relatively quiet. Others remained compact because quasar activity expelled gas before it could form new stars. TON 618's quasar likely influenced its galaxy in ways that we can only infer. The balance between feeding the black hole and forming stars would have determined the structure of that galaxy. Even though we cannot observe the host galaxy of TON 618 directly, the quasar reveals enough to suggest that it existed in a highly dynamic state. The quasar era was full of galaxies undergoing rapid changes. Their shapes were irregular. Their star formation rates fluctuated. Their gas reservoirs were in constant motion. When galaxies merged, their shapes distorted. When quasars ignited, gas was heated and pushed away. The environment itself was part of the story. The universe was more chaotic, structures were less settled. Into this chaos, black holes like TON 618 grew with remarkable efficiency. As the universe aged, the quasar era gradually faded. The number of active quasars declined. The universe entered a long period of slower, steadier evolution. Clusters formed, galaxies stabilized, cooling flows shaped the movement of gas. Black holes continued to grow, but at a slower pace. Phoenix A emerged in this world, not from the explosive growth of early quasars, but from the quiet accumulation of mass over billions of years in a cluster environment. Comparing it with TON 618 becomes easier when you understand their origins. One belongs to a time of intense acceleration. The other belongs to a time of long pacing. Seeing the quasar era as the environment that shaped TON 618 provides context for its mass. It wasn't simply that the black hole grew rapidly, it was that the entire universe participated in that growth. Dense gas, frequent collisions, and high star formation rates created conditions where rapid feeding was almost inevitable for black holes placed in the right regions. TON 618's extreme mass reflects an environment capable of producing extremes. Looking at this era helps explain why such black holes become markers in cosmic history. They show us that the early universe was not only active but efficient at creating massive structures. They show us how quickly matter could gather. They show us the role of quasars in shaping galaxies. They show us the difference between youthful cosmic conditions and the more stable conditions of later times. Approaching Phoenix A requires letting go of the expectations built by the quasar era. If the early universe resembles a crowded, energetic city filled with noise, motion, and constant construction, then Phoenix A's world is more like a vast, quiet district built after centuries of development, where everything has found its place and change happens subtly. The region around Phoenix A does not blaze with the intense radiation of rapid accretion. It does not announce itself through bright flares or powerful optical signatures. Instead, it sits within the center of a massive galaxy cluster, surrounded by hot gas and long-standing gravitational structures that move on timescales almost impossible to imagine. The quiet darkness around Phoenix A is not emptiness. It is the product of an environment that has settled, stabilized, and matured into something far different from the turbulence that shaped black holes like TON 618. Descending toward Phoenix A means entering a space dominated less by the flashy displays of a quasar and more by the slow, steady mechanics of cluster physics. The Phoenix cluster is one of the most massive and active clusters known, not because it is youthful in the same sense as the early universe, but because it hosts unusually strong cooling flows. The gas between galaxies in the cluster is incredibly hot, heated to millions of degrees by gravitational interactions. This gas emits X-rays, making the core shine at wavelengths we cannot see with our eyes. In many clusters, the central black hole produces enough energy to keep this gas from cooling rapidly. But in the Phoenix cluster, the balance leans in a different direction. The gas cools more quickly than typical, allowing it to flow inward. That inward flow provides material for star formation, and for the central black hole, even though the feeding process looks nothing like the dramatic accretion disks of the quasar era. This cooling flow contributes to the faint but steady activity at the centre of the cluster. The material drifting inward does not form a bright quasar. It does not ignite a luminous disk with emission lines stretching across the spectrum. Instead, the inflowing gas forms a more subdued structure. Some of it cools enough to form new stars in the central galaxy. Some of it becomes part of the long-term feeding cycles that sustain Phoenix A's black hole. These processes unfold over hundreds of millions of years. They do not create the immediate brilliance we associate with quasars, but they do maintain a slow and persistent pathway for mass to reach the centre. Moving deeper into the cluster, the light takes on a different character. Instead of bright quasar emission, you find the glow of X-ray radiation from the intracluster gas. Telescopes that observe in these wavelengths reveal complex structures, bubbles carved by past jets, shock fronts indicating earlier periods of activity, and long filaments of cooler gas stretching inward. These filaments are particularly interesting because they show how cooling gas can condense along narrow paths. They guide material toward the centre, creating channels through which Phoenix A's black hole receives a steady supply. Unlike the chaotic feeding of early quasars, this process resembles a long, slow river of gas flowing inward through a quiet basin. When you move closer to the central galaxy, the environment changes again. The stars in the core move in patterns shaped by the combined gravity of the galaxy and the black hole at its centre. Their orbits are influenced by a mass that is far beyond the scale of ordinary supermassive black holes. Phoenix A's mass sits in the uppermost range known, making its gravitational presence a major force in shaping the movement of stars in the central region. These motions offer clues about the black hole's size, even though no bright accretion disk gives a straightforward measurement. The central galaxy of the Phoenix cluster is enormous. It is the brightest galaxy in the cluster, and it has grown through repeated mergers over billions of years. Each merger added stars, gas, and sometimes another black hole. Over time, these black holes spiraled inward until they merged with the central black hole. Each merger contributed mass. Each merger altered the gravitational structure slightly. Through this ongoing process, Phoenix A acquired a complex history written into the motions and distributions of its stars. Descending toward the black hole itself, the environment becomes quieter, not in a literal sense, but in the sense that the energy output is less visible. Instead of the bright radiation of an accretion disk, you encounter structures shaped by past activity. Cavities carved into the hot gas offer evidence of powerful jets launched during earlier episodes. These cavities show where the black hole once injected energy into the surrounding environment, heating the gas and slowing the cooling flow. Even though Phoenix A is not currently shining as a quasar, these remnants of earlier activity demonstrate that the black hole has gone through active phases. The jets that carved these cavities did not create optical brilliance, but they produced enormous mechanical energy. that energy transferred into the surrounding gas, pushing it outward and creating space where the density is lower. As the gas flows back into these cavities, it changes temperature, density, and motion. These effects create a dynamic but understated interplay between the black hole and the cluster. They reveal how Phoenix A influences its environment even without the dramatic signals usually associated with accretion. As you descend further, important differences become clear. Ton 6 Huygens light reveals its presence from across the cosmos. Phoenix A's influence is seen through interactions rather than illumination. The black hole itself is almost entirely hidden. It does not shine. It does not outline itself with glowing gas. It is a gravitational core at the center of a region filled with matter shaped by its pull. The quiet darkness around it does not imply inactivity, but rather a different mode of existence, one where energy transfers occur more gently, where feeding happens gradually, and where the structures marking past activity fade slowly into the broader tapestry of the cluster. Another aspect of descending toward Phoenix A involves the recognition that this black hole grows not through rapid bursts of feeding, but through steady accumulation. The cluster environment provides gas consistently, but at rates far below what would be required for a luminous quasar. Phoenix A's growth reflects patience rather than urgency. The inflowing gas moves downward through temperature gradients, cooling enough to become denser but not cooling so quickly that it forms a bright accretion disk. Instead, it forms streams and clouds that gradually spiral inward. The dynamics of this slow feeding reveal a process that is spread across immense stretches of time. As you come closer to the central region, the temperature of the gas changes significantly. The gas in the cluster can remain at tens of millions of degrees, but the inflowing streams cool to lower temperatures as they move inward. Observations of these cooling filaments show that they extend for hundreds of thousands of light years. They act almost like cosmic rivers, channeling gas toward the central galaxy. These structures are among the reasons the Phoenix cluster forms stars at an unusually high rate. As the gas cools, it reaches conditions suitable for forming new stars. The central galaxy appears to be undergoing one of the highest star formation rates observed in any cluster. This rate reflects not only the cooling gas, but the balance between feeding the black hole and forming stars. Descending deeper brings you closer to the region where the gas becomes dense enough to be influenced directly by the black hole's gravity. The stars in the central bulge move at high velocities. Their paths reflect the mass at the center, and by observing these motions, astronomers approximate the mass of Phoenix A. These star motions offer some of the most concrete evidence of the black hole's size. Even though the black hole itself is invisible, the motions around it reveal its scale. The gravitational pull required to keep stars moving at such speeds points to a mass that fits within the category of the most massive black holes known. As the descent continues, the complexity increases. The interactions between the black hole and the surrounding gas create patterns that reflect long cycles of cooling and heating. When the gas cools and flows inward, the black hole eventually receives enough material to ignite a new episode of energy release. That energy heats the gas again, creating a temporary balance that slows the cooling. But in the Phoenix cluster, the cooling is unusually strong, which means the black hole must go through cycles more frequently or more intensely. These cycles leave behind structures such as shock fronts and cavities, which reveal the history of activity. Even within this quiet environment, traces of earlier dynamism remain. Radio observations reveal regions where electrons accelerated by jets emit radiation long after the jets themselves have faded. These radio signatures outline the pathways carved by the jets. They show how far the influence of the black hole extends. They also show how the cluster gas responds to these injections of energy. The radio structures help scientists estimate the power of past jets, which in turn helps estimate the amount of mass accreted during those episodes. Approaching the event horizon itself does not provide visual clues. There is no bright disk illuminating the edge. Instead, the region is filled with diffuse gas, low in density and dim in emission. The black hole sits in the center, shaping everything around it through gravity alone. This gravitational presence is the defining feature of Phoenix A's quiet darkness. It shapes the cluster by regulating the flow of gas. It shapes the central galaxy by anchoring its structure. It shapes the motion of stars by dominating the central potential well. Descending into this environment brings into focus how different Phoenix A is from black holes observed during the quasar era. Its growth is not marked by blazing light, but by gravitational influence and long-term cycles. Its presence is not seen directly, but interpreted through the structures it creates. Its environment is not chaotic but stable, filled with hot gas that moves slowly across vast distances. The quiet darkness becomes a reflection of an advanced cosmic age, where early galaxies created rapid growth, clusters create slow accumulation. The difference between brightness and darkness becomes one of activity, not mass. A black hole can be incredibly massive and still remain faint. The light surrounding it depends on how much material is currently falling inward. Phoenix A does not require high feeding rates to maintain its influence. It has already reached a size where its gravitational effects dominate the central region. Whether lit or dark, its presence is unmistakable through the structures it shapes. Moving through the complex environment of the Phoenix cluster shows how varied the paths to extreme mass can be. TON 618 reached its size through early, intense feeding. Phoenix A reached its size through slow, steady merging and cooling flows. One grew quickly in a young universe. The other grew gradually in a settled one. The descent toward Phoenix A's quiet darkness marks the contrast between these two histories. When trying to grasp the scale of something like TON 618 or Phoenix A, it often helps to move away from the numbers for a moment. Numbers become difficult at this level. They stretch into ranges where the difference between billions and tens of billions stops feeling meaningful. Instead, imagining the physical boundary of each black hole, the event horizon, brings the scale into clearer focus. The event horizon is not a surface in the traditional sense. It's not a place where matter collects. It isn't a shell you can touch or a structure you can map with conventional tools. It is a boundary defined by what can and cannot escape. If light crosses that boundary, it cannot return. The strength of gravity becomes so absolute that escape is no longer possible. Even though the event horizon is invisible, the radius that defines it comes directly from the mass of the black hole, and that radius grows in proportion to the mass. This is why black holes such as TON 618 and Phoenix A can have event horizons large enough to encompass entire star systems. The simplest way to think about the size of an event horizon is through the Schwarzschild radius, which calculates how large the boundary would be for a non-rotating black hole of a given mass. In real life, many black holes spin, so the details become more complicated. But for understanding the scale, the Schwarzschild radius offers a clear, direct way to see how mass translates into size. For every solar mass, the Schwarzschild radius is about 3 kilometers. That number seems small, almost trivial, until you begin stacking it billions of times. A single solar mass creates a radius of 3 kilometers. 1 million solar masses create a radius of 3 million kilometers. 1 billion solar masses create a radius of 3 billion kilometers. Once you reach tens of billions of solar masses, you're dealing with boundaries that dwarf the scale of planetary systems. TON 618, with a mass exceeding 60 billion solar masses, has an event horizon so large that it stretches into territory we rarely discuss in ordinary astronomy. Even comparing it to the orbit of a planet feels inadequate. The event horizon could extend beyond the orbit of Neptune if placed at the centre of our solar system. It might even reach farther, depending on the precise mass estimate used. This radius defines the region where nothing can return. It is not an object you can approach and observe in the usual sense. There is no surface. There is no material boundary. There is only the point at which escape becomes impossible. Phoenix A's event horizon is also enormous, though its exact radius depends on the final mass estimate used. As one of the heaviest black holes known in a relatively nearby cluster, its event horizon spans distances that still exceed the orbits of planets in our solar system many times over. Even if Phoenix A's mass is lower than TON 618's, its event horizon remains far beyond any scale we experience directly. It defines a region where the geometry of space becomes so curved that paths of light bend sharply, and anything crossing the boundary cannot re-emerge. One of the strange things about event horizons is how unremarkable they appear to objects falling toward them. Someone falling in, setting aside the impossibility of surviving such conditions, would not encounter a physical obstacle, wall, or surface. They would simply cross a threshold where the rules governing motion shift in a fundamental way. The boundary is mathematical, not structural, but its size and shape are controlled entirely by the mass inside. That mass curves space around it, creating the conditions that define the horizon. When the mass reaches tens of billions of solar masses, the curvature extends extraordinarily far. Imagining an event horizon the size of a star system raises questions about what happens near that boundary. The gravitational pull at the event horizon of a supermassive black hole is strong, but the tidal forces, meaning the difference in gravitational pull across an object, are surprisingly gentle compared to smaller black holes. In a stellar mass black hole, the tidal forces near the event horizon are intense enough to stretch objects dramatically, but for black holes as large as TON 618 or Phoenix A, the event horizon is so far from the centre that the tidal differences become smaller. Crossing the horizon itself, if one could do so without being affected by other hazards, would not feel like being torn apart. The danger lies deeper inside, where the curvature becomes more extreme. This surprising gentleness near the horizon is part of what makes supermassive black holes distinct. Their gravitational field is strong, but the gradients are low. The difference between the inward pull at one end of an ordinary spacecraft or a human body and the other end would be small enough to pass unnoticed. This is not the case near smaller black holes, where the gradient becomes so extreme that objects would be pulled apart long before reaching the horizon. With giants like TON 618 and Phoenix A, the boundary becomes more of a subtle threshold than a violent barrier. Still, the size of the event horizon means that light paths behave in unfamiliar ways. Light that comes close, but does not cross the boundary, can orbit the black hole in what is sometimes called the photon sphere. This region is not stable for long-term orbits, but light can circle the black hole briefly before escaping outward. The larger the black hole, the larger this orbiting region becomes. For TON 618, this photon orbit would exist far outside the Schwarzschild radius, creating a vast zone where paths of light distort dramatically. The scale of these distortions becomes part of how scientists interpret the environment around supermassive black holes. When telescopes observe the brightness of a quasar, or the shape of radiation near a black hole, part of what they see is influenced by how space is bent. The bending of light, known as gravitational lensing, becomes extreme near a giant black hole. Even if we cannot observe the event horizon directly, we can observe how light behaves near it. Simulations show that the region just outside the horizon forms a bright ring of distorted light. This ring results from photons that orbit partially around the black hole before escaping. In TON 618's case, the accretion disk during its quasar phase would have been so luminous that this distorted region would produce a strong signal. The bending of light would spread the emission into complex patterns, contributing to the broadening of spectral lines and the intensity of the quasar. Phoenix A, with its quieter environment, does not produce such brilliant illumination around the horizon today. But the same gravitational effects still shape the movement of matter and the pathways of light. Even in darkness, the horizon defines the architecture of the space around it. Another way to visualize the scale is to think about how long it takes light to cross the event horizon. For a stellar mass black hole, light crosses the radius almost instantly. For a supermassive black hole, the crossing time becomes longer. For TON 618, it could take many hours for light to cross the diameter of the event horizon. This detail highlights how large the region is. Even though nothing can escape from inside the boundary, the distance across that boundary remains governed by the speed of light and the mass of the black hole. The fact that TON 618 and Phoenix A have event horizons on the scale of star systems also affects how their host galaxies behave. The gravitational pull near the centre becomes a dominant force on the orbits of nearby stars. Large regions of the central galaxy respond not to the mass of millions of stars around them, but to the single concentrated mass at the heart. This influence extends outward far beyond the event horizon, shaping the entire central structure of the galaxy or cluster. In the Phoenix cluster, the central galaxy is so large that its structure blends with the intracluster medium. The presence of Phoenix A influences the motion of stars across wide regions. Even stars thousands of light years away feel the pull of the central mass. TON 618 likely exerted similar influence on its host galaxy during its quasar phase. The gravity of these giants shapes the evolution of entire systems, not just the space immediately around them. Event horizons also play a role in how black holes merge. When two supermassive black holes spiral inward, their event horizons eventually touch. Once that boundary is crossed, the black holes merge into a larger one with a new combined horizon. This merging process releases gravitational waves, ripples in the curvature of space that propagate outward. These waves are detectable by instruments like LIGO and Virgo for smaller black holes. For giants like Phoenix A or TON 618, mergers produce gravitational waves at frequencies lower than current detectors can measure, but future observatories may eventually detect such events. When two event horizons of this size combine, the resulting boundary becomes even larger, creating a single, more massive black hole. Imagining horizons on these scales also highlights how black holes interact with gas clouds. Gas that drifts inward far from the event horizon behaves differently from gas near the boundary. Far outside the horizon, gas may orbit for millions of years, forming disks or streams. As it falls inward, it heats and accelerates. But near the event horizon, its motion becomes dominated entirely by the curvature of space. If the feeding rate is high, the region outside the event horizon lights up dramatically. If the feeding rate is low, the event horizon sits quietly with little activity visible around it. Phoenix A's current quietness shows how a black hole can have an enormous event horizon yet appear faint. Without a brightly feeding disk, the horizon remains hidden, its presence revealed only through indirect signs, such as the motion of stars and the shape of gas structures. TON 618, by contrast, shines because of its accretion disk. Its event horizon might be even more dramatic, but the brightness of the quasar obscures the boundary itself. We do not see the horizon, we see the gas outside it. Another aspect of horizon size involves gravitational time dilation. Time passes differently near such a massive object. For someone far away, clocks near the event horizon appear to run slowly. This effect becomes more dramatic the closer one moves toward the boundary. For black holes with event horizons the size of star systems, the region where significant time dilation occurs is vast. Gas orbiting near the horizon experiences time in a different way than gas far outside it. The interplay between time dilation and orbital motion affects the shape of the accretion disk and the behavior of matter near the black hole. Even though the event horizon is a boundary that nothing can cross outward, its size remains meaningful for understanding the scale of the black hole's influence. The horizon marks the point where gravity becomes absolute. Beyond that boundary, the core of the black hole holds all of its mass in an incredibly compressed region. The surrounding space responds to that mass through curvature. This curvature guides the movement of stars, gas, and light. Thinking about star system-sized event horizons makes it easier to understand how black holes like TON 618 and Phoenix A become central anchors. They are not just large objects. They are structures that define the architecture of their environments. They shape the motion of matter across vast distances, They regulate gas flows, they influence star formation. Their horizons mark the inner boundary of a gravitational influence that extends outward across regions so large they become difficult to describe. As these horizons grow through feeding and mergers, the space they occupy expands. Each additional solar mass increases the radius slightly. Over billions of years, this growth produces the extreme sizes we see today. TON 618's horizon reflects rapid early growth. Phoenix A's reflects long-term patience. Both horizons represent journeys through cosmic history, shaped by conditions that differ dramatically, but guided by the same physics. Trying to imagine what it would be like to fall toward a black hole the size of TON 618 or Phoenix A means entering a part of physics where intuition stops being useful. Everything we experience, motion, light, time, gravity, behaves differently as you approach a region governed by such extreme curvature of space. Even so, thinking slowly through the process can reveal what distinguishes these giant black holes from the smaller ones found in ordinary galaxies. Unlike the violent tidal forces you might expect from the kind of black hole formed from a collapsing star, the environment near a supermassive black hole's event horizon becomes strangely gentle. The quietness is deceptive because it masks the gravity that ultimately directs everything inward. But in terms of the physical sensations an object might encounter as it falls, the scale of these giants softens the experience rather than intensifying it. If you started from far away, drifting toward either TON 618 or Phoenix A, the early part of the journey would feel uneventful. At such distances, the gravitational influence of the black hole would blend with the gravity of surrounding stars and gas. You would be inside a region shaped by the larger galaxy or cluster, rather than by the black hole alone. Your motion would follow paths determined by the overall structure around you. Only as you move closer would the central mass begin to dominate. The gravitational pull would slowly become more aligned toward the center, and the surrounding stars would appear to shift position as your path gradually curved inward. During this approach, time would still feel normal to you, but to a distant observer, your motion would begin to look slower. This difference marks the first steps toward gravitational time dilation. The effect grows stronger the closer you come to the event horizon. If you carried a clock with you, it would tick at the usual pace from your perspective, but someone observing from far away would see that same clock ticking more slowly than theirs. This difference is not a trick or illusion. It reflects the real way time changes in the presence of strong gravitational fields. For supermassive black holes, the region where time dilation becomes noticeable is enormous, stretching across distances measured in billions of kilometers. As you continue inward, the gravitational pull begins to guide you more directly. Unlike orbiting near a smaller black hole, where tidal forces would stretch objects violently long before crossing the horizon, the tidal forces around TON 618 or Phoenix A remain surprisingly small at this stage. The reason is simple. Tidal forces depend on the gradient in gravity, not just the overall strength of the pull. Because the event horizon of a giant black hole sits far from its center, the gradient across an object remains low. Your head and your feet would experience almost the same gravitational pull. You would not feel stretched. You would not feel crushed. You would simply fall, as if moving through empty space. The strange part is how little sensation accompanies such an extreme environment. Even though you would be falling at high speed, you would feel weightless. Falling removes the sensation of weight because weight only appears when something prevents you from falling. In empty space, falling feels like drifting. In that sense, the approach toward the horizon becomes quiet in a physical and sensory way. There is no sound. There is no resistance. The motion feels natural because gravity does not push. It guides. If you looked outward during this approach, the view would shift in ways that violate everyday expectations. Light from distant stars would begin to distort. Gravitational lensing would bend their paths, making some stars appear to stretch into arcs or thin curves. Regions of space behind the black hole would seem to wrap upward and around, creating the illusion that distant light sources are appearing in places where they should not exist. This distortion grows more intense the closer you move toward the photon orbit region, where light can circle the black hole once or twice before escaping. For black holes as large as TON 618, this region lies at significant distance from the horizon. The brightness of the accretion disk during the quasar era would have made this region glow with intense light. Phoenix A, being quieter now, offers less illumination, so the view would be darker. But the distortions would still exist because the geometry of space depends on mass, not light. Even in a quiet cluster core, the bending of starlight would reveal the black hole's presence long before reaching the boundary. As you approach the photon orbit, the distortions of light become more dramatic. Light from behind you could be bent forward. Light from above could appear below. The sky would begin to compress toward a smaller area ahead of you. The black hole itself would appear as a dark sphere growing in size, surrounded by a thin, bright ring of distorted light. For TON 618, that ring would stretch across a breathtaking portion of your view, because the photon orbit encloses a region larger than the diameter of the solar system. For Phoenix A, the effect would be similarly vast, though the brightness might differ depending on local gas and dust. By this point in the fall, time dilation becomes significant. If someone far away watched your descent, they would see your motion slowing even though you experience no such change. To them, your clock would be ticking at a slower rate. To you, everything would remain consistent. Nothing in your body would slow. Nothing would signal that time was stretching relative to the outside world. It is only from the perspective of someone at a distance that your motion would appear to fade towards stillness. If you kept falling inward, eventually you would pass close to the region where tidal forces begin to increase. But even here, the increase happens slowly. For stellar mass black holes, the gradient becomes extreme within small distances. For supermassive black holes, it remains moderate until well inside the event horizon. The approach feels nothing like the destructive imagery often associated with black holes. It is quiet. It is weightless. It is smooth. The moment you reach the event horizon is where the most dramatic differences between internal and external perspectives occur. From your perspective, nothing unusual happens. You drift across the boundary, and the moment passes without sensation. There is no surface to strike, no barrier to break, no bright flash. The event horizon is not a physical structure, so crossing it feels identical to the space just outside it. But from an external point of view, this is the point where your image would freeze. Someone watching from far away would see your descent slow until it nearly stops. Your clock would appear frozen. Your light would become dimmer and more redshifted. Eventually your image would fade into darkness. But this fading is an effect of the way light behaves near the horizon, not an indication of anything happening to you at that moment. Once inside the event horizon, the geometry of space changes in a way that is difficult to visualize. The direction you experience as forward no longer leads outward. Every possible path becomes directed inward. There is no direction that allows escape. Even if you attempted to accelerate outward, the structure of space-time would prevent it. Inside this boundary, all possible motions lead toward the core. Despite the inevitability of the inward path, tidal forces remain relatively small for giants like TON 618 or Phoenix A until you move closer toward the center. That means an object could travel for a significant amount of time inside the horizon before encountering destructive forces. The journey inside is not long in terms of physical distance, but time dilation and the curvature of space-time affect how that motion unfolds. For massive black holes, the region inside the horizon remains large compared to the same region inside smaller black holes. Light inside the event horizon behaves in unfamiliar ways. Outward travelling light still moves outward relative to you, but mathematically it follows paths that lead inward. This contradiction reflects the difference between local perception and global geometry. Locally, the speed of light remains the same. Globally, the curvature of space forces those paths to bend. If you carried a flashlight and shined it outward, the The beam would appear normal to you, but its path would curve irreversibly toward the center. You would not see darkness in front of you. You would see light behaving normally. Yet all of it would be directed toward a single destination. The deeper you fall inside the horizon, the more the curvature of space intensifies. Eventually, tidal forces would increase enough to stretch or compress objects. For giant black holes, this stage occurs much closer to the center. Ton 618's immense size creates a large interior region where tidal forces remain gentle. Phoenix A's interior would also be sizable. The difference between these giants lies in their masses, not in the experience of crossing the horizon. What makes these falls fascinating is the silence. Not just literal silence. Space has no medium for sound, but the silence of physics acting without drama. Nothing announces the crossing of the boundary. Nothing announces the increase in curvature. Nothing alerts the falling object to the change in time relative to the outside world. Everything happens smoothly because the scale is so enormous. Even though no object can escape from the inside, the fall itself is not violent until the very end. The concept of spaghettification, the stretching of objects due to tidal forces, is associated with small black holes. For giants like Ton 618, the stretching becomes intense only near the core. A falling object has more time before reaching that region, though the exact duration depends on the starting point, the motion, and the curvature of space at that mass scale. Understanding what it feels like to fall in requires acknowledging the gap between intuition and physics. Intuition tells us that a fall into a black hole must be sudden, destructive, and chaotic. Physics tells us that the initial stages are nothing like that for supermassive black holes. They're gentle, they're slow in terms of tidal change, they involve no abrupt sensation at the horizon. The chaos lies in the last fraction of the journey, not the first. Thinking about falling into Ton 618 also highlights the difference between brightness and gravity. During its quasar era, the region outside the horizon would have been extremely luminous, but the horizon itself would have remained invisible. Falling in during that period would mean passing through layers of bright hot gas, experiencing intense radiation long before reaching the boundary. Phoenix A, by contrast, provides little illumination today. The environment around its horizon is quieter. Falling in would occur in relative darkness, guided only by the motion of stars and the shape of space. The final moments inside the horizon cannot be observed from outside. No information escapes. The internal structure remains hidden by the boundary. But the inward fall, when imagined from the standpoint of general relativity, provides a glimpse into how gravity acts when scaled to such extraordinary masses. Time, light, and motion change their relationships. The horizon becomes a mathematical divide rather than a physical barrier. The journey becomes a path where the rules shift gradually, not abruptly. Thinking about these falls helps reveal the deeper contrast between Ton 618 and Phoenix A. One grew during a brilliant, turbulent era filled with light. The other grew quietly, shaped by long-term cycles. Yet inside the horizon, both follow the same physics. No matter how different their histories or surroundings may be, the inward journey converges into the same inevitable geometry of space-time. Understanding how giants like Ton 618 and Phoenix A are even possible means stepping back from individual black holes and looking at the universe as a whole. Their existence is not a simple matter of accumulating mass. It requires a set of cosmic conditions that unfold over billions of years, shaped by physics that begins at the earliest moments after the Big Bang. These conditions do not just allow extreme black holes to form, they make them almost inevitable in certain parts of the universe. When you look at these processes slowly, one at a time, the picture becomes clearer. The universe is not merely a backdrop where enormous black holes appear. It is the architect that provides the materials, the timing, and the mechanisms that allow those black holes to reach sizes that challenge the idea of scale. The first requirement is the formation of matter itself. In the seconds after the Big Bang, the universe was a seething mixture of energy, particles, and radiation. It expanded rapidly, cooled gradually, and eventually reached a point where particles could form stable atoms. That early stage shaped everything that followed. Without the right combination of matter, dark matter, and radiation, gravitational structures could not have formed. Black holes rely on gravitational collapse, and gravitational collapse relies on matter collecting in particular patterns. As the universe expanded, small fluctuations in density, tiny differences caused by quantum variations stretched across enormous distances, created the seeds for future structures. These fluctuations became the skeleton from which galaxies, clusters, and eventually supermassive black holes would grow. The next essential piece is dark matter. Even though we cannot see it directly, dark matter provides the gravitational scaffolding for galaxies. It forms large halos that gather ordinary matter through gravity. Without dark matter, the universe would expand too quickly for galaxies to take shape. There would be no stable regions dense enough for stars to form. And without stars, there would be no stellar remnants to collapse into black hole seeds. Dark matter does not interact with light, but shapes the motion of matter on large scales. It creates the gravitational wells where gas collects, cools, and forms the first stars. These stars then explode or collapse, leaving behind the earliest black holes. Every supermassive black hole in the universe has grown inside a dark matter halo, even if we cannot see that halo. Once the earliest stars formed, they lived fast, violent lives. The first generation of stars is thought to have been massive, much larger than typical stars today. These early stars burned hot and short. Their cores fused elements quickly. Some ended in supernova explosions that seeded the universe with heavier elements. Others collapsed directly into black holes. These initial black holes became the first seeds that could, under the right conditions, grow into something far larger. Their growth depended on the availability of gas and the structure of the galaxies around them. The early universe had no shortage of gas. Everything had only recently cooled enough for atoms to form. This abundance created opportunities for rapid feeding. The growth of black holes also required the universe to remain dense enough for gas to fall inward rather than disperse. During the first few billion years, galaxies were small and full of gas. They collided frequently. Their shapes were irregular. Their centers were chaotic. This chaos was essential. It funneled material towards central regions. Gas does not fall inward without some kind of disturbance. It must lose angular momentum. Collisions between galaxies, interactions between gas clouds, and turbulence created the conditions needed for gas to settle toward the center. Each inflow event gave black holes more material to consume. This is why the quasar era occurred early in cosmic history rather than later. Another requirement is that the universe must evolve in a way that allows black holes to merge. When galaxies collide, their black holes do not immediately combine. They orbit each other. They spiral inward slowly over hundreds of millions of years. Each merger increases the total mass. Over the course of cosmic time, a black hole can grow through multiple mergers. This process is essential for creating the most massive black holes. Feeding through gas can produce a significant amount of growth, but mergers provide an additional mechanism that becomes more important in large galaxies and clusters. Phoenix A likely grew through many such mergers. Each merger altered its structure slightly, adding mass to the central black hole. The universe also provides mechanisms that regulate feeding, so that black holes do not grow uncontrollably. Radiation emitted from accreting gas pushes outward, slowing the rate of inflow. Jets launched from the central regions heat surrounding gas, preventing it from cooling too quickly. These feedback processes shape the relationship between black holes and their environments. Without feedback, black holes might grow even faster, but galaxy structures would be disrupted. Feedback allows black holes to grow, while also shaping the galaxies and clusters around them. It creates cycles of feeding and quiet periods. These cycles help explain why black holes like Phoenix A can coexist with stable galaxy clusters, yet still reach enormous masses over time. Another factor in the universe's ability to produce such giants is the structure of the cosmic web. Galaxies do not drift through space randomly. They are connected by filaments of gas and dark matter. These filaments act as channels guiding matter toward galaxy clusters. As gas flows along these cosmic highways, it collects in the densest regions. Black holes at the centers of these regions receive a steady supply of material over billions of years. Phoenix A's cluster sits at a point where multiple filaments converge. That convergence provides a continuous stream of gas that can cool and feed the central galaxy. This long-term supply is essential for producing a black hole of its size. Even the expansion of the universe plays a role. As the universe expands, galaxies grow farther apart. This expansion reduces the frequency of major collisions over time. In the early universe, collisions were common. That is one reason why black holes grew rapidly during the quasar era. Later, collisions became less frequent, but clusters remained bound by gravity, even as the universe expanded around them. Within these clusters, galaxies continued to interact. This provided an environment where black holes like Phoenix A could continue growing long after the quasar era had ended elsewhere. The cluster environment extends the timeline for growth, allowing black holes to accumulate mass gradually over billions of years. The cooling of gas inside clusters is another essential piece of the puzzle. In many clusters, the central black hole produces enough energy to keep the gas hot, preventing rapid cooling. But in the Phoenix cluster, the cooling rate is unusually high. This rapid cooling forms streams and filaments that flow inward. The fact that the gas can cool at this rate means that material continues to reach the central galaxy, and eventually the black hole. Without this cooling, the gas would remain hot and diffuse. Phoenix A would receive less material. The cluster's unique balance between cooling flows and heating processes allows the black hole to grow beyond ordinary expectations. TON 618's existence highlights another aspect of the universe: the timing of large-scale structure formation. In the early universe, structures formed quickly. Gas fell into dark matter halos at high rates. Star formation occurred at extraordinary levels. These conditions created a fertile environment for the growth of hypermassive black holes. The early universe acted like a cosmic forge, producing extremes that the later universe cannot replicate easily. By the time the universe expanded enough to reduce these opportunities, objects like TON 618 had already reached remarkable sizes. Their masses became locked into place by time and distance. This ability of the universe to create giants depends on multiple overlapping processes. Matter must exist in sufficient quantities. Dark matter must shape gravitational wells. Gas must cool. Stars must form and die. Black holes must seed themselves. Galaxies must collide. Feedback must regulate growth without halting it. Clusters must trap gas and galaxies within their gravitational fields. The cosmic web must funnel material towards central regions. The universe must evolve at the right pace to allow these stages to unfold. Each of these elements acts across immense timescales. Human experience makes it difficult to grasp how long these processes take. Billions of years pass before the largest black holes reach their final sizes. A black hole gaining mass slowly over time might accumulate only a small amount over the course of 1,000,000 years. But multiply that by 1,000 million years, and the total becomes enormous. This steady accumulation is part of the universe's long patience. It does not rush. It does not produce extremes through sudden bursts alone. It builds them through the layering of slow processes over cosmic history. Another part of the universe's role is stability. Even though the early universe was chaotic, it was also governed by predictable physics. Gravity acted consistently. Gas followed known laws of thermodynamics. Stars fused elements according to well-understood processes. This predictability allowed structures to form in recognizable patterns. Black holes formed wherever conditions allowed it. Over time, the distribution of matter shaped the growth of galaxies and their central masses. The universe does not need to intervene or adjust. Its laws govern the formation of structures automatically. When viewed this way, the existence of extreme black holes becomes less surprising. They are not exceptions. They are the result of the universe operating as it always does. TON 618 grew because it existed in an environment with unusually favourable conditions early in cosmic history. Phoenix A grew because it lived in a massive cluster that continued supplying gas and merging galaxies. The universe set the stage for both. It provided the materials, it provided the time, it provided the physics. Seeing the universe as the architect of these giants also helps explain why such extreme objects become tools for studying cosmic evolution. Their masses reflect the environments they grew in. Their brightness or quietness reveals the activity around them. Their influence shapes the structures that contain them. They become records written across billions of years. TON 618 records the intensity of the early universe. Phoenix A records the long-term accumulation inside clusters. Each tells a story not only about itself, but about the universe that allowed it to form. When you look carefully at black holes as large as TON 618 and Phoenix A, they begin to act not only as astronomical objects but as historical records. Their sizes, environments, and behaviours are shaped by the state of the universe at different times. They carry the imprint of events that happened long before Earth formed, long before the Milky Way took shape, and long before the structures familiar to us today came into existence. These giants serve as markers along the timeline of cosmic evolution. Each of them tells a different story about how the universe has changed, what conditions existed at certain epochs, and how matter has flowed through the cosmos over billions of years. By studying them, you begin to see the broader patterns that define cosmic history. TON 618 is a window into the early universe, a time when everything was more compact, dynamic, and energetic. Its mass, its quasar brightness, and its distance all point toward the universe's most active era. When its light began travelling toward us, galaxies were still forming and merging at high rates. Gas clouds were everywhere. The cosmic web had not yet stretched into its current configuration. The universe was only a few billion years old. In that environment, extreme growth was possible. TON 618's existence indicates that some black holes were able to take advantage of these early conditions, feeding quickly and efficiently during a period when the supply of cold gas was enormous. The brightness we see from TON 618 is not simply the glow of a distant object. It is a message sent from a younger cosmos. The broad emission lines reveal the velocity of gas swirling around the black hole, telling us that the structure was already immense at a time when most galaxies were still assembling. The fact that we can observe that light now means that the quasar was powerful enough to project its signal across more than 10 billion years of expansion. As the universe stretched, the wavelengths of its light stretched with it. The redshift tells us exactly how far back in time we're looking. When you place that information on the timeline of cosmic history, TON 618 becomes a landmark. It marks a moment in the universe's youth when intense feeding created black holes that would remain among the largest known. Phoenix A, on the other hand, occupies a very different part of the universe's timeline. It exists in a cluster that formed over billions of years. Its mass reflects not rapid early growth, but long-term accumulation. Over time, galaxies merged at the cluster's centre. Their stars blended with the central population. Their black holes spiralled inward and eventually combined with the growing central black hole. The cooling flows within the Phoenix cluster continued feeding gas into the core, adding more mass little by little. Each of these processes unfolded over extended spans of cosmic time, shaped by the slow evolution of the universe after the quasar era had faded. The contrast between TON 618 and Phoenix A tells us how the universe changed as it aged. In the early universe, rapid growth was common because everything was close together. Galaxies interacted often. Gas cooled quickly. Gravity had not yet stretched the cosmic web to the vast scales seen today. Hyperluminous quasars were abundant because the feeding environment was ideal. Black holes could reach extreme sizes within relatively short cosmic intervals. TON 618's existence reveals that some structures formed astonishingly quickly, far earlier than one might predict based solely on current cosmological conditions. Phoenix A reflects the later universe, where large-scale structures such as galaxy clusters dominate. The expansion of the universe slowed the rate of galaxy interactions outside of clusters, but inside clusters, gravity continued pulling galaxies together. The cluster environment became a stable, long-term engine for growth. Phoenix A's mass reveals that clusters can act as reservoirs of matter long after the quasar era ends. They show that extreme black holes can reach enormous sizes, not only through rapid feeding in the early universe, but through steady accumulation in mature cosmic environments. These two paths, rapid early growth and slow late growth, mirror the broader evolution of the universe. Early cosmic history is defined by rapid changes. Stars form quickly, galaxies grow explosively, structures emerge from turbulence. Later cosmic history is defined by stability, cooling, and gradual transformation. Clusters form, galaxies settle. Black holes like Phoenix A grow quietly instead of blazing as quasars. Each era contributes differently to the growth of cosmic structures. Another element that these giants reveal is the role of environment in shaping cosmic history. TON 618 formed in a galaxy likely rich with gas and undergoing intense star formation. Its host galaxy probably experienced multiple mergers. These interactions drove gas toward the center, creating the perfect conditions for rapid accretion. Phoenix A formed in a central cluster galaxy, surrounded by hot gas extending across hundreds of thousands of light-years. The gas cooled slowly, forming streams that brought material inward. Although the environment was quieter, the long-term supply of gas and repeated mergers eventually produced a black hole of extreme size. This difference in environment reflects how matter becomes distributed as the universe evolves. In the early universe, dense regions of gas existed in many galaxies. In the later universe, gas becomes concentrated in the intra-cluster medium. TON 618's fuel came from its galaxy's internal gas. Phoenix A's fuel comes from the broader cluster environment. These differences reveal how the universe reorganizes matter over time. Black holes like these also tell us something about the cosmic web. TON 618's presence suggests that some dark matter halos in the early universe were unusually efficient at funneling gas into their centers. This efficiency allowed the early growth of massive black hole seeds. Phoenix A's cluster environment reveals how cosmic filaments channel gas into large gravitational wells over billions of years. These filaments supply clusters with material that continues feeding central galaxies long after individual galaxies have exhausted their gas. The cosmic web, therefore, plays a central role in producing extreme black holes across different eras. Another piece of cosmic history revealed by these giants involves feedback processes. Quasars release enormous amounts of energy. That energy heats surrounding gas, regulates star formation, and influences the evolution of galaxies. TON 618's quasar likely produced winds strong enough to push gas outward from its host galaxy. These winds help explain why some galaxies stop forming stars earlier than others. Phoenix A shows a different kind of feedback. Its jets carve cavities in the cluster gas, injecting energy that prevents runaway cooling. These two types of feedback, quasar winds and cluster heating, illustrate how black holes influence their environments differently at different times in cosmic history. The behavior of these giants also shows how galaxies evolve. TON 618 in his host galaxy likely grew rapidly, forming stars at high rates before its quasar pushed gas outward. That early star formation enriched the galaxy with heavier elements, shaping its future evolution. Phoenix A's galaxy grew through mergers. Each merger added stars, changed the distribution of mass, and contributed to the overall structure of the central region. These patterns mirror the broader shift in galaxy evolution from early starburst activity to later merging activity in clusters. Cosmic history is also written in the way these black holes interact with light. TON 618's quasar shows that the early universe was filled with luminous energetic sources that reveal the distribution of gas and matter through absorption lines in their spectra. These lines show what the intervening universe looked like at that time. Phoenix A being dimmer relies on X-ray emissions from the cluster gas to reveal its environment. These X-ray signals show how gas behaves in the later universe. They reveal cooling flows, cavities carved by jets, and the temperature structure of the cluster. In both cases, the light, or the lack of it, carries information about the state of the cosmos at vastly different times. One of the deeper insights these giants offer is that the universe is not static in its ability to form extreme objects. Early conditions favoured one type of giant, later conditions favoured another. TON 618 shows what happens when the universe is young, dense and full of raw material. Phoenix A shows what happens when the universe is old, structured, and dominated by clusters. Both represent natural outcomes of cosmic evolution. Neither is an exception or anomaly. They are products of the physics that unfolded across enormous time. These black holes also highlight how cosmic history is cumulative. Every generation of stars contributes elements to the next. Every merger reshapes galaxies. Every cooling flow redistributes matter. Every quasar blast clears space for future growth. Each stage builds on the previous ones. TON 618 formed from environments shaped by the first stars and early galaxy assembly. Phoenix A formed from environments shaped by billions of years of mergers and gas dynamics. Their masses reflect the layered history beneath them. Even their sizes reflect the timeline of the universe. A 60 billion solar mass black hole like TON 618 indicates that the early universe allowed rapid mass accumulation. Phoenix A's similar magnitude indicates that long-term processes in clusters can eventually match those early growth rates. Their horizons stretch across distances far larger than planetary orbits because the universe had time to supply them with enough material. Their existence tells us that the universe is capable of producing structures that greatly exceed the scale of galaxies themselves. When examined closely, TON 618 and Phoenix A become complementary records. TON 618 shows the height of early cosmic activity. Phoenix A shows the endurance of long-term cosmic evolution. Together, they reveal that the universe shapes its largest structures through both the explosive energy of youth and the steady accumulation of age. They are products of a universe that changes, cools, stabilizes, and continues building over billions upon billions of years. Trying to make sense of something as large as TON 618 or Phoenix A eventually brings you face to face with the limits of human scale. Our lives unfold on such small stages compared to the structures the universe builds. We measure our surroundings in meters or kilometers. We think about hours and days, even when we stretch into bigger numbers such as the distance to the moon or the length of a year. Those scales remain close to us. They're familiar enough that we can imagine them without strain. But the universe refuses to confine itself to those comfortable boundaries. It creates structures that exceed every intuitive frame we carry. It stretches masses across billions of solar equivalents. It shapes distances measured in trillions of kilometers. It unfolds over timescales so long that words like ancient begin to lose definition. And yet somehow, the human mind continues to reach outward, trying to understand forces and sizes that were never meant to fit inside our everyday experience. This is what gives objects like TON 618 and Phoenix A their unusual power. They are not only physical structures, they are reminders of how small our ordinary frames of reference are. Not in a discouraging way, but in a way that expands perspective gently. When you think about an event horizon that could swallow entire star systems, or a black hole that formed when the universe was only a fraction of its current age, you're forced to widen the lens through which you view existence. The numbers no longer tell the whole story. The images no longer offer easy comparisons. You begin to feel the scale instead of calculate it. Something shifts internally as you realize how much there is beyond anything human senses evolved to process. And yet, there is calmness in that realization. Instead of feeling lost, many people feel comfort in the enormity. It becomes a kind of soft mystery, one that doesn't demand answers but invites reflection. Ton 618 and Phoenix sit so far away and their masses are so large that the usual instinct to measure or categorize begins to quiet down. Instead of trying to fit them into some mental diagram of planetary orbits or galactic maps, you find yourself stepping back and simply accepting that there are structures in the universe whose scale operates beyond any practical comprehension. It's not necessary to understand them fully to feel the presence they represent. This shift often creates a kind of gentle humility, not the kind that diminishes human significance, but the kind that places human experience within a broader context. A black hole growing over billions of years is not a threat to human meaning. If anything, it reminds us that the universe has space for both extremes, vast cosmic structures and small conscious moments like the one you're having now. The contrast does not minimize either side. Instead, it shows that scale does not define value. A galaxy-spanning structure can exist, and so can a quiet evening with someone listening to a soft explanation about the nature of the cosmos. The mystery of scale also connects us to time in a different way. When thinking about the mass of Ton 618, you're thinking about something that existed in full force billions of years before Earth took shape. Its quasar shone when the universe was young enough that galaxies were still learning how to assemble themselves. The light that reaches us now is a memory of that time, travelling across an expanding universe. Phoenix A's mass reflects processes that continued long after. It is the product of countless mergers, cooling flows, and gravitational cycles that unfolded while planets formed, life emerged, species evolved, and civilizations grew. Even though these giants seem impossibly distant, their histories include the same timeline that led to the present moment. They are not separate from our story. They are part of the same universe that produced us. Thinking about these timelines creates a sense of continuity. When you look at Ton 618's light, you are looking at something that left its source long before humanity existed. When you consider Phoenix A's slow growth in the heart of a cluster, you are contemplating a process that continued through all of Earth's history. Scale becomes not only a matter of distance or mass, but a matter of time. Understanding these objects requires acknowledging that our own lives are short frames in a much larger sequence, and yet our curiosity allows us to reach across that sequence, tracing the faint signals from ancient quasars and the subtle patterns in cluster gas. This ability to interpret vast scales is unique. No other species we know of contemplates the growth of black holes or the evolution of galaxy clusters. No other species measures light that has travelled billions of years to reach them. Even though we occupy a tiny corner of the universe, we have developed the tools and the perspective to understand structures so large they seem almost beyond imagination. The fact that we can comprehend even parts of them becomes a quiet triumph. It reminds us that the universe is not merely indifferent space, it is something we can explore intellectually, even from a small planet orbiting a quiet star. When thinking about scale, it also becomes clear how interconnected everything is. Black holes like Ton 618 and Phoenix A do not sit apart from the rest of the cosmos. They're shaped by the flow of matter through galaxies. They're influenced by the expansion of the universe. They depend on dark matter halos. They emerge from the deaths of massive stars and the merging of galaxies, and they in turn influence their surroundings, regulating star formation, shaping cluster structures and releasing energy across enormous distances. These giants are woven into the universe in ways that reflect the same laws of physics that govern atoms, planets, and biological systems. Nothing about them is separate from the underlying fabric. Their size does not make them exceptions. Instead, they are results of the universe applying its rules across greater scales. Recognizing this continuity makes the universe feel more unified. It shifts the narrative away from seeing cosmic structures as distant curiosities and towards seeing them as natural outcomes of the same processes that allow stars to shine and planets to form. It also highlights how small-scale life fits into the broader picture. Humans may never experience gravitational time dilation near an event horizon or witness a galaxy merger directly, but our existence depends on earlier events that followed the same physical laws. The elements in our bodies were forged in stars. Those stars were influenced by the gravitational pull of black holes and dark matter. Those black holes formed from earlier stars in earlier galaxies. Scale becomes less of a separation and more of a chain. Another aspect of this soft mystery involves the way our minds create meaning from scale. When people first hear the mass of Ton 618 or Phoenix A, the reaction might be to interpret them as intimidating or overwhelming. But when you move slowly through the nature of their formation, when you understand how the universe produces them through ordinary physics acting over extraordinary time, the intimidation softens. They stop being monsters and start being markers. They become reminders of cosmic patience and of processes that continue regardless of whether anyone is there to observe them. There is also a quiet reassurance in knowing that the universe is larger than any single event. When you think about personal concerns, stresses, or uncertainties, they often feel enormous within the context of daily life. But placing them against the backdrop of galaxies, clusters, and ancient black holes can ease the sense of urgency. Not because those concerns don't matter, but because scale provides perspective. It shows that existence operates on many levels at once. Some are local and immediate, others extend across billions of years. Both can coexist without negating each other. This perspective also opens space for reflection about what it means to be conscious in a universe like this. Black holes do not think about their growth. They do not reflect on their origins. They do not experience the passage of time, yet they shape their surroundings profoundly. Humans, by contrast, do not shape galaxies, but we observe them, we interpret them, we contemplate their meaning. In that sense, consciousness itself becomes a kind of scale, not physical scale, but the scale of awareness. The ability to hold the image of a star system-sized event horizon in the mind is its own kind of achievement, even if that image remains faint or incomplete. The mystery of scale also includes the way we perceive distance. Light from Ton 618 travelled for more than 10 billion years before reaching Earth. That distance is hard to grasp, not because the number is too large, but because we have no personal reference for what it means. We can imagine a long walk or a long drive or even a long space mission, but we cannot imagine crossing billions of light years. The universe works at scales where human travel becomes irrelevant, and yet our instruments bring those distances into reach. Telescopes gather the light, spectrographs analyze it, computers process the data. We end up holding information from the distant past in the palms of our hands. That is another way the mystery becomes soft rather than overwhelming. It also helps to remember that the universe feels enormous because we are measuring it from within. If you were an observer who existed on a cosmic timescale, the distance between one galaxy and another might feel small. If your awareness lasted billions of years, the growth of a black hole might seem quick. Scale depends on perspective. A star's lifetime seems long to us, but short compared to the age of the universe. A human lifetime seems long when lived day by day, but brief when compared to cosmic structures. And still, during that brief span, we can understand enough to connect ourselves to the larger story. This connection does not require minimizing ourselves. It requires recognizing that the universe is not divided into important and unimportant scales. It contains everything from the behavior of subatomic particles to the evolution of galaxy clusters. All of it operates under the same set of principles. Ton 618 and Phoenix A exist because the universe follows rules consistently across all sizes. Human beings exist for the same reason. We emerge from the same physics. Our thoughts, movements, and experiences fit into the same cosmic framework. Thinking about scale can also bring a sense of peace. When you picture these giants, you're picturing structures that have existed for longer than any civilization, any species, or any landscape on Earth. They persist through cosmic cycles without urgency. They grow slowly. They shape their surroundings calmly. They remain untouched by the frantic pace of daily life. There is something reassuring in that difference. The universe does not rush. Even when creating its largest structures, it takes its time. It allows billions of years to pass without hurry. That patience becomes part of the lesson embedded within these giants. The final realization that emerges from contemplating scale is that the universe does not limit our ability to understand it. Even from a small planet orbiting a quiet star, we can follow the light of ancient quasars, map clusters, measure masses, and interpret signals sent across unimaginable distances. Our scale does not prevent comprehension. It simply means that understanding requires imagination, patience, and the willingness to stretch beyond familiar boundaries. If you sit with that idea long enough, the enormity of Ton 618 and Phoenix A begins to feel less like a contradiction of human scale and more like an expansion of it. When you think about them, you are participating in something far larger than yourself. You are connecting to the history of the universe through thought alone. That connection does not require physical travel. It does not require matching their size. It only requires awareness.